the chair of this morning's session, Beatrice Bonga. Thanks very much for chairing, and I will stop talking.
Yeah, good morning, everyone. This morning is all, well, like Aaron nicely said in the email, second order fest with a strong representation from Southampton. And Adam will kick it off. So for all speakers of this morning, I'll just write in the chat a 5-minute warning and a 1-minute warning. And then if you really go way over, I'll just interrupt you. But I hope that won't be necessary. Adam, the floor is all yours.
Okay, thanks, Beatrice, and thanks, Aaron, for organizing the meeting. I guess I don't have my video on. That's fine. Okay, so I'm really going to cover kind of 2 separate topics here based on collaborations with 2 different groups of people. So the first topic is going to be how to generate waveforms with the 2 timescale expansion. So that'll go back to stuff we were talking about yesterday. And then the second half will be the concrete calculations that I've been doing with my former student, Jeremy Miller, Niels Warburton, and Barry Wardell forever. We give you an update every single year on the same calculations. And we have some nice results to report this year. Okay, so first, why do we care about second order? Most people I talk to outside of the Capra community are amazed we even care about first order. They usually ask me, why don't we just use post-Newtonian theory to model MREs? But we do need very high accuracy for these things. So these, of course, are the systems we're interested in. A small mass little m going around a big mass capital M. Small mass perturbs the background metric of the big mass. And you have this power series in the mass ratio, where I'm using epsilon to denote the small mass ratio. Okay, then why do we need second order? Well, basically because the inspiral lasts such a long time of order 1 over the mass ratio that any small error you make effectively gets multiplied by 1 over the mass ratio because it accumulates over time. So even if you have an error of 10 to the minus 6, if you multiply that by 10 to the 6, all of a sudden you're at an error of order 1 in your phase. So let's say the trajectory of the small object is described by an equation of motion like this. We have a first order self-force or self-acceleration term, and second order, and so on to higher orders. And then just consider the effect of the second order term on the position of the small body. So let's say that drives a small correction delta z. So that delta z has an acceleration of order epsilon squared. Then we just naively integrate this twice to get a change in the position of order epsilon squared times time squared. And so then that time is so huge, it's of order 1 over epsilon, that all of a sudden you have an order 1 correction to your position, and therefore an order 1 correction to your orbital phase and your gravitational waveform phase. So obviously we cannot neglect something of order 1. That might be 2 radians, that might be 10 radians, that might be 0.75 radians, we don't know what it is, but unless for some reason it's numerically small, we can't neglect it. And the evidence suggests that it is not numerically small. Okay, so we need second order to model MREs. There's also another good motivation to go to higher order beyond first order, and that's to help improve models of intermediate mass ratio inspirals and similar mass binaries. So this has been a big business over the last decade of trying to use different binary models to improve each other. That's been done a lot at first order. And recently, Damore has published some pretty incredible results showing that if you had a second order calculation, you would actually fully fix the 5 pn two-body dynamics and the 6 pm two-body dynamics. So you get very high order information in the weak field just by going to second order in the strong field. There's also the possibility of using self-force to directly model more comparable mass binaries. So specifically MREs, but maybe even more comparable mass than that. So obviously the higher order you go, the more accurate you're going to be. And then you could hope you could push perturbation theory and self-force to the left in this diagram. And Martin Vanderment is going to show some pretty spectacular results tomorrow, I think, or maybe the next day, I can't remember, suggesting that second-order self-force calculation is really incredibly accurate, or potentially incredibly accurate, well towards the comparable mass regime, much closer than you'd expect to comparable masses. Okay, regardless of whether you're modeling MREs or IMREs, you have some basic scaling arguments telling you what you need from first order and second order to get particular accuracy in your phasing. So on an in-spiral timescale of order 1 over epsilon, Hinder and Flanagan showed a long time ago that the gravitational wave phase has an expansion that looks like this. So at leading order, it's 1 over epsilon. That's because the phase accumulates roughly linearly in time. So after a time of order 1 over epsilon, you have a phase of order 1 over epsilon. And this leading order term, phi 0, is called adiabatic order in the phase. And we expect that just that should be enough to detect most signals. And we might not even need that. It's not sure if we know yet. But then for precise parameter extraction, you really need to make sure that your errors are small. So you need this order 1 term. So this term is roughly independent of the mass ratio. And you're going to need it if you want to make sure that your errors in your phase are much less than a radian. So this is called the first post-adiabatic order. And what do you need for each order? For adiabatic order, all you need is the averaged dissipative piece of the first order self-force. And we have efficient algorithms for calculating that, although that's still, despite being in existence for 16 odd years now, 15, that actually still hasn't been implemented for generic in-spirals and Kerr. Now for first post-adiabatic order, well, we need all the rest of first order self-force. So we need the conservative piece and the oscillations in the dissipative piece. And then we need the averaged, so the time averaged dissipative piece of the second order force. Now, what I really want to emphasize here is that the second order piece is just as significant as the first order piece. So it's not a matter of pushing the accuracy even higher. It's equally important as the first order conservative piece. So this community has been calculating that conservative piece for 2 decades now. And if you've been, spending your time doing that, then you've got to realize that we need the second order piece just as much as the first order piece. And we can't actually expect the first order piece to improve our phasing at all unless we also have the second order piece. So it is really critical to have this. Okay, now how do we calculate it? This is a summary of second order self-force theory. So the basic idea is we model the small object as a moving puncture in the field equations. So it's a singularity in the space-time represented by this puncture field. We move the puncture field to the right-hand side of the field equations and treat it as a source for this smooth residual field. And so this method is derived rigorously from matched asymptotic expansions, but I'm not going to get into the derivation. I'm just going to start from these equations. So first order, you only sourced by the puncture. And that's completely equivalent to writing that the full H1 is sourced by a point particle. At second order, you're again sourced by the puncture, but now you also have quadratic combinations of the first order field sourcing your second order field. And then these residual fields you calculate go into the equation of motion for the puncture. So these punctures are moving on the world line governed by this equation. So here we have things that are linear in the residual field and things that are quadratic in the residual field. And the punctures look roughly like this. First order puncture diverges as 1 over distance from the world line as you approach the world line Z. Second order puncture diverges as 1 over distance squared. So as you go up in orders, you get more and more singular. And then subleading order, you have the mass times the residual field. Okay, so what we want to do is solve for these residual fields and then use them to drive the motion. And the way this is written, you'd have to do this as a coupled system. You'd have to solve this in the time domain, moving the world line forward according to this equation, and then solving the field equations at every time step. Now that's potentially possible, but that is not the method that we are pursuing. Most of the calculations at first order, particularly in Kerr, are based on frequency domain. They're not based on time domain. And so the idea here is that this is a typical calculation at first order. You say, okay, I've got a few constants of motion. I have the energy, the angular momentum, and the Carter constant for a generic orbit in Kerr. And then expand my first order metric perturbation in a Fourier series. So this is appropriate for a bound orbit where you have a discrete frequency spectrum. So you have a radial frequency, a polar frequency, and an azimuthal frequency. And this is just evolving, the phases here are just evolving linearly in time. And then your amplitudes of these frequency modes depend on the values of your system parameters, these constants of motion. And then the evolution of your orbital parameters is very, very simple if written in appropriate variables. The phases, as I said, are just omega times t. So that's, if you solve this, it's just omega times t, because these j's are constant in time. So these are the constants of motion. You write your frequencies in terms of the constants of motion, and then your phases are just frequency times time. Okay, but now that obviously can't last for a long time. That can't be good for a whole in-spiral because the frequencies change with time. And so you don't expect to have a Fourier series like this. So instead, we use a 2-timescale expansion, where now we have a bigger list of system parameters. We still have energy, angular momentum, and Carter constant, but now also over a long time scale, there's a small correction to the mass of the big black hole and a small correction to its spin that are both evolving slowly with time. And so then what I wrote on the previous slide was only at first order. What I'm writing here is for arbitrary order. And what we have is amplitudes that depend only on these system parameters, and then phase variables. So we have rapidly oscillating phases and slowly evolving amplitudes. Now, how do we know this is slowly evolving and this is quickly evolving? We have to choose our parameters such that that's true. So we choose system parameters that satisfy equations like this. So t tilde is the slow time, epsilon t. And you have forcing functions that are driving the slow evolution. These forcing functions don't depend explicitly on t tilde. They only depend on system parameters themselves. Then your phase variables are governed by frequencies that are constructed from your system parameters. And again, there's no explicit time dependence. So this is a frequency that's purely slowly evolving, and then you just integrate over time to get the phase. Now, how do you put this into practice? Well, you substitute that ansatz into your field equations, and then when you operate with time derivatives, if the time derivative acts on the phase, you just bring down a factor of the frequency. So this omega k is kr times omega r plus k theta times omega theta plus k phi times omega phi. So if you act on the phases, you just bring down a frequency. If you act on the system parameters inside the amplitudes, those are slowly evolving, so you bring out a factor of epsilon because the time derivative is small. So this j dot is a slow time derivative, not an ordinary time derivative. And then just chain rule, you have derivatives of the amplitudes with respect to system parameters. Now, the key thing here is that the phases all factor out of the equations. They all disappear from the equations. So if you start with equations like this, you end up with just frequency domain equations, where everything only depends on the frequencies and everything is slowly evolving. Now, this relates back to what I was talking about yesterday, that you actually need to do near identity transforms as a pre-processing step in order to do second order, because you need to get your variables to be slowly evolving. If you have rapidly evolving phases here, then this is not going to be slowly evolving equations, and your 2 timescale expansion is actually broken. It doesn't work. Okay, so what's the big picture for waveform generation? Well, you compute those amplitudes, that are functions of the system parameters. You compute the frequencies as functions of the system parameters, and you compute those driving terms as functions of the system parameters, all across the parameter space. Then once you have all these 3 things, well, then you basically just immediately spit out a waveform by solving these very simple ODEs. And everything is slowly varying here. You don't need to sample any rapid oscillations. Now, this is the picture that Michael showed yesterday of this waveform generation framework. And so what I want to point out here is that in order to do the post-adiabatic calculations, we really need to hugely expand the pre-processing step to cover pretty much everything. We need to do the nits first. We need to do everything first as a pre-processing step, and then it can feed into a fast waveform generation. Okay, now very, very quickly, what have we done with quasi-circular orbits? So this is the case that we've been talking about for years. In this particular case, we have a simple set of system parameters, just the orbital radius, the slowly changing mass of the big black hole, slowly changing spin, and your field just has one phase variable, which is the azimuthal phase, which is just an integral of the azimuthal frequency. So then the frequencies appearing in your field equations are just azimuthal mode number times azimuthal frequency. So this is supposed to be a simple test case, but we've been working on this one case for 8 years and it's still kicking. I think I have time for everything. Okay, so when we substitute that relatively simple ansatz into these equations, what do we get? We get a frequency domain equation for the first order field, frequency domain equation for the second order field. The equations of motion split up into a sequence of equations for the evolution of the orbital radius and how the orbital frequency relates to the orbital radius. And then these punctures get somewhat smoothed out because we're breaking everything up into modes, and the integrations smooth out the singularity somewhat. So the key thing that appears here is this nonlinear coupling of first order modes to generate the second order source, and these derivatives of the first order field with respect to the orbital parameters. Okay, so here's the latest results we have. These are the second order energy fluxes at infinity. And this is a comparison of the contribution from a particular mode, the 4-4 mode of the second order field, comparing it to the post-Newtonian approximation. This is just the leading post-Newtonian approximation from the literature. The blue curve is the leading order flux that everybody's calculated many times. The orange dots are the new results. These are the subleading fluxes, the second order fluxes. And you see they agree with the PN result just as well as the first order fluxes agree with the PN result. So this is for the 4-4 mode. I was just picking modes randomly here, but again, it works just as well for the 5-4 mode. So everything is working for these modes. And I was hoping to show these. Yeah.
Just so that you know, you have 1 minute out of your 20 left.
Perfect. No time for questions, just the way I like it. Okay, yeah, I was hoping to show some exciting waveforms We do have waveforms, but they're not exciting because we know they're broken a little bit. If anyone wants to see the waveforms that we do have, I'm happy to show you them. Okay, but just quickly to summarize, the 2-time scale expansion provides an efficient framework for generating post-adiabatic waveforms. And the native outputs from the expansion are already in the form suitable for accelerated waveform production. They're already knitted, everything's already done, and is a pre-processing step within the calculation itself. There's still some work to do for quasi-circular orbits in Schwarzschild, but we do have fluxes working. Waveforms hopefully will be soon. And there was a paper out on the general method yesterday. Okay, the extension to eccentric orbits also looks feasible. There's a talk by Ben later today showing that. But we still have a lot of problems. Calculating the second order source is ridiculously expensive. There'll be some talks later today and tomorrow suggesting ways of making it less expensive. All of this talk was in the Lorentz gauge in Schwarzschild, but that's not good in Kerr. And we have some talks by my student Andrew Spiers, Stephen Green, and Peter Zimmerman about possible ways to go to Kerr. Another problem is that we just calculate too much. We're currently calculating the entire second order metric perturbation, the entire cell force, everything. We don't need all that. All we need is the averaged dissipative force. And we are working towards getting a quick scheme for calculating that. And Zeyd Sam will talk about that later today. Okay, sorry, I'm over time.
Thank you, Adam. I guess indeed, in your spirit, since you don't like questions, I guess we'll still allow one question, and otherwise, the rest of the people, I guess, get all the hard questions.
Okay.
Anyone? If you want, I don't see any questions. Well, I guess the rest of the people will be thrown under the bus, I guess. Great. Andrew, can you share your slides? Thanks again, Adam, for this very clear and nice talk.
Thanks, Beatrice.
Andrew, go ahead. The floor is all yours.
Oh, am I mute still?
I hear you now.
Okay, good. Great, okay. Should I jump into it?
Sure, go ahead.
Hello, everyone. I'm Andrew Spiers. I just want to say thank you to the organizers and thank you for all logging on to watch this talk. I hope you enjoy it. Today, I'm going to talk about progress on second order cell force in Kerr. This is work with my supervisor, Adam Pound, and collaborator, Jordan Monson. Okay, a quick overview of what I'm going to discuss. We're going to try and extend the first order methods in Kerr to second order, so specifically the Tucholsky equation. Then I'm going to have a look at gauge and gauge invariance at second order and why it's more complicated than at first order. And following that, I'm going to discuss a scheme for fixing to good gauges in the physically significant regions. So as Adam's just discussed, second order calculations have begun, and that's for quasi-circular orbits in Schwarzschild, and they've already got some results. Now in Kerr, as Adam said, in the Lorentz gauge, the Einstein field equations are non-separable. So we're going to need a new method. So let's take a look back at first order cell force in Kerr and try to extend it to formalize a method that works at second order in Kerr. So a quick note on my notation is I'm going to absorb the mass ratio epsilons into these superscripts. I'm going to be talking about psi4 a lot, which is the fourth file scalar, which is a curvature scalar. And just here that the full psi4 is the sum of the background psi4 and its perturbations. Okay, so first order cell force in Kerr. Well, current methods involve solving the Tucholsky equation, which is a differential operator, here I write as O, acting on the first order perturbation to psi4. And on the right-hand side, it is sourced by a linear operator acting on the first order perturbation to the stress energy tensor. Now, importantly, this O can be made separable, which makes it practical for numerically calculating Psi4-1. Now, once you have Psi4-1, how do you get a hold of the cell force? Current methods use CCK metric reconstruction, where you can calculate from Psi4 a Hertz potential, and then from the Hertz potential, you can calculate the metric perturbation, and the metric perturbation gives you the first order cell force. Now we want to extend these methods to second order so that we can calculate the second order cell force. And as Adam said, we specifically want the dissipative piece of the second order cell force, which can be given by the second order perturbation to Psi4-2 alone, we believe, up to maybe the evolution of the Carter constant. We're unsure if we can calculate that from Psi4-2, but I'll leave that for another talk. Okay, so the second order Tucholsky equation has actually been around for about 20 years. A version was derived by Campanelli and Lousteau, where you see you've got this familiar operator acting on Psi4-2 now, a similar source, and this additional source term, which is a quadratic operator acting on perturbations to the Newman-Penrose scalars. Now, what you need to know about SLC is that it's quadratic in H1. So each of these terms depend on H1. And when you try to apply this equation to the gravitational cell force problem, you experience a problem at the world line because the metric perturbation is singular at the world line. So this makes the source SLC very singular, r to the -6 roughly. When you try and integrate this source term, you'll see that you get an ill-defined answer. So here on the world line, where r is distance from the world line, when you evaluate on the world line, this is undefined, so r equals 0. So that motivated us to try and find a new second order Tucholsky equations whose source we can make regular. Now I'm going to show you a quick derivation of our equation. And to do that, I'm going to need the spin -2 Wald identity. And you'll see that the Wald identity simply falls out from the Tucholsky equation, where we've defined this operator T as when it acts on H1, it gives you Psi4-1. And we've used the linearized Einstein equation here as well to give you this familiar OT equals SE operator identity. So if we instead act on H2, and you'll see that what drops out is another Tucholsky-like second order equation. Now we are operating on this quantity Psi4L2 instead, which is defined as T acting on H2. The source is a bit more simple, perhaps. Now it's only acted on by the linear operator S, which is in the original Tucholsky equation. And we've used the second order linearized Einstein equation to give you this additional quadratic Einstein operator term here. Okay, so what is this Psi4L2? To understand that, it came up in Campanelli and Lousteau's paper as well. Take a look at Psi4-2. So you see Psi4-2 is defined as a piece which is linear in H2 and a piece which is quadratic in H1. And Psi4L2 is simply just the linear in H2 piece. So Psi4L2 contains all the H2 information as Psi4-2. And importantly, at Scribe Plus, the leading order behavior is the same for Psi4L2 as Psi4-2, which also is the piece which holds the information about the dissipative piece of the gravitational waves. So you can collect the information about the energy and angular momentum being dissipated away to Scribe Plus, which I should say is asymptotic null infinity. So it's where all the radiation goes when it leaves the system. And Zeyd Sam is going to talk more about that later. A useful property of Psi4L2 is that unlike Psi4-2, it is infinitesimal tetrad rotation invariant. This is sort of similar to local Lorentz invariance, and it makes comparing results more easy. So we've got a new second order Tarkovsky equation, how do we make the source regular? Is it regular? So first we take a look at the singular nature of the second order stress energy tensor is confined to the world line. So off the world line, T2 equals 0. But on the world line, we need to handle it so we can introduce a puncture scheme where you've got this psi4L puncture. And that means you're solving just for the psi4L2 residual piece, which is the piece which contains the self-force information. We've still got this singular term, S d2g. And how singular is it? Well, in the highly regular gauge, we see it's similarly highly singular with 1 over r to the 5 dependency. So you might think that doesn't look very integrable either. However, we can use the fact that S is a linear operator. And in the highly regular gauge, d2g, the most singular part of d2g, also acts as a linear operator acting on h1. And from distribution theory, we know that linear operators acting on distributions give you a distribution. So therefore, this S d2g in the highly regular gauge is well defined as a distribution and is therefore integrable. Okay, so now I'd like to take the last 5 minutes or so of my talk to discuss gauge invariance at second order. So say we've got an equation to give you a second order quantity, but is it gauge invariant? At first order, life is made easy because psi4-1, which you solve the Tarkovsky equation for, is gauge invariant. And you can see that here by the gauge transformation equation. Because psi4-0 is 0 in Kerr spacetime, because it's type D, then psi4 in the new gauge equals psi4 in the old gauge. It is gauge invariant. This property is not shared by psi4-2, because as you see, the gauge transformation equation is much more complicated at second order. You've got this first order gauge terms coming in and a second order gauge vector term. Now you can make this psi4-0 equals 0 simplification, which simplifies this equation, but it's not gauge invariant. And I should say that this property is shared by psi4L2. I'm just going to talk about psi4-2 here to keep things simple. But we can use this simplification that this second order gauge vector has fallen out from our equation. Therefore, for gauge fixing, we only need to calculate the first order gauge vector. So gauge fixing is specifying your results to a specific gauge with no residual gauge freedom. So it's sort of akin to gauge invariance if you can't find an actual gauge invariant quantity. So now I want to talk about gauge fixing, which again came up in Campanelli and Lousteau's paper, and they gave a method which involved solving PDEs. We wanted a slightly more practical method. And we also wanted to consider the gauge fixing in the Emery problem. So here I've got a little Penrose diagram of an Emery spiral inspiring into the black hole at H+, and you see it's emitting radiation to Scry+, asymptotic null infinity. And as I discussed earlier, at the world line, gamma, you want to be in the highly regular gauge. So we've got this dark blue here around the world line, which is cyan blue. And then you want to analyze the gravitational waves being emitted into the supermassive black hole. So you want to analyze the energy and angular momentum being emitted there. So you want a horizon regular gauge near the black hole horizon. And to analyze the radiation being emitted to Scry+, you want an asymptotically flat gauge. So now I'm going to talk about our method for fixing to an asymptotically flat gauge, specifically the Bondi-Sachs gauge. So a brief introduction, the Bondi-Sachs gauge was developed to actually analyze gravitational waves. And it basically builds space-times out of null cones of constant retarded time u. So you see you've got constant retarded time along inside this whole gray region, this gray cone. And also the null rays along the cone have constant angular component. And this gives you these gauge conditions that the RR and RA component is 0. There's an additional gauge condition, which we don't really need to worry about here on the angular metric. So how do you fix to the Bondi-Sachs gauge? And we have developed a method for doing so in perturbation theory. So we, again, remember that we only need to calculate Z1. So we take a look at how the metric transforms under a gauge transformation. So this prime is in the new gauge, and we constrain H prime such that it satisfies the Bondi-Sachs gauge conditions. And so you can take any H1 that you have in any gauge, and we want to solve this equation for Z1. Now what we found is that solving this equation for Z1 reduces to solving a hierarchical set of ODEs backwards from Scribe+ along null rays. So basically on Scribe+, you eliminate all the non-Bondi-Sachs behavior with Z, and then you integrate into the space-time along null rays. However, constraining to the Bondi-Sachs gauge is not sufficient because there are some residual gauge freedoms associated with the mapping of Scribe+ to itself. So this is the BMS group, so the deformations under which Scribe+ can map to itself, and that's an infinitely amount of freedoms in that group because of the super translations you might have heard of. So then we decided to try and fix the BMS frame of the space-time. So we found that we can constrain it algebraically up to the time and axial rotation symmetries of the Kerr background space-time. So you can't constrain these freedoms naturally. And but to constrain the infinite many other freedoms, you can place constraints on the UU and the UA components of H prime. So if you implement these two methods into our second order Tucholsky equation, then you set it up such that it solves for psi4L2 prime. So this is psi4L2 in the Bondi-Sachs gauge in a fixed BMS frame. So no matter what your inputs to this equation are in, you get the same results out. So it's practically a gauge invariant. Quick advertisement for some talks tomorrow. There's the additional problem that H1 calculations use CCK metric reconstruction, and they have pathological singularities associated to the radiation gauge. So Stephen Green is going to talk about his work with Hollands and Zimmerman, where they have extended metric reconstruction to non-vacuum spacetime. And following that talk, Peter Zimmerman is giving another talk on work with myself, Green, Pound, and that is implementing the formalism that Stephen Green is going to talk about for a point particle in flat space. And that's with the aim to ameliorate these singularities for second order calculations. So thank you very much for listening. Just a summary that I've given a new second order Tucholsky equation, which we think we can regularize. I've talked about gauge fixing to 3 significant regions, and I've given a method for fixing to the Bondi-Sachs gauge and fixing the BMS frame. Thank you very much for listening, and please contact me if you have any questions.
Thank you, Andrew. That was very nice and interesting. Anyone, any questions about this talk? Wow, I do. I see some raised hands. Yes. Yen, go ahead and ask your question.
Hello, can you hear me?
Yeah.
Okay. I'm just confused about the operators. Is that a general operator or something physical meaning? Yes, the O and S. I just forgot that.
Okay, so this is the Tucholsky equation for psi4-1.
Yes.
So if do you know of the Tucholsky master equation, master operator? Do you know of that?
Yeah.
So to get that from this O, you need to factor out a factor of rho to the -4 in front and -4 at the back. And you can rearrange it to get the master Tucholsky equation.
Okay, thank you. And you said the second order gauge is not the gauge invariance. It's just it's in the whole spacetime or just in the asymptotic flat region, or
That's in the whole space-time.
in the whole spacetime.
Yeah.
So we just use the bounded Sachs gauge to fix the gauge invariance, right?
Yeah. So the information you want is at scribe plus, so it's enough to fix it so that it's fixed at scribe plus, because then you can get the gauge invariant information out of psi4 too.
Okay. Thank you. Okay.
I see another question by Wojciech. Go ahead.
Hi, Andrew. So my question is, do you have some kind of physical interpretation for the BMS frame fixing, or how should we understand?
Okay. So the BMS frame is pure gauge. So really, I don't think there's any physical representation in this case. But it's akin to, so you have, it's like in Euclidean space, you can fix where the origin of your coordinates are. So you, in the BMS fixing, you do that, but you also fix other freedoms which involve the super translations. So it's just fixing even more freedoms, if that makes sense. But I'm not exactly sure the physical interpretation of the super translations because they are pure gauge.
Great.
Okay,
thank you, Andrew. I think it's time to move on to our next speaker. Sam, could you pull up your slides?
Thank you.
I'll clap again for you. That was very clear.
Bye.
All right, just sharing my screen. Okay.
The floor is all yours.
Great. Thank you very much. So yes, my name's Sam Upton, and today I'll be talking about work that I've been doing with my supervisor, Adam Pound, on second order gravitational self-force in a highly regular gauge. And I'd like to thank as well the organizers for the opportunity to give this talk. So as Adam mentioned previously, the second order is crucial for LISA. So I'm not going to go over that again. And one of the major hurdles that we find at second order is the strong divergences near the small objects world line. So generically, a second order singular field would go like m squared over r squared, where r is the distance to the small objects world line. Now, this causes a lot of problems with defining things well, or when we do numerical integrations, they can take a long time because of the strong divergence. However, it was previously shown by Pound that there exists, that in the highly regular gauge, the singular field only goes like m squared over r. So this alleviates a lot of our problems. It's much better for numerics because it diverges less to a less extreme manner. And also from this, we can actually define things in a rigorous way distributionally, which allows us to define the second order stress energy tensor, which we call the Detweiler stress energy tensor for reasons that will become clear. So only the leading order of the highly regular gauge, the 1 over r piece, was presented in this paper here, but we've extended that to order r as required for numerics. So I briefly want to go over the principle of matched asymptotic expansions because this is crucial for understanding why we can define a highly regular gauge. So say here we have G exact. So this describes the whole space-time with the big black hole and the small black hole. So on the scale of the big black hole, there are perturbations caused by the small black hole, which we write down here with the little h's cause the perturbations caused by the small black hole. But we can also expand our full metric near the small object, where the perturbations are caused by the curvature caused by the big black hole. Now, of course, these are just two expansions of the same spacetime, so there should be some region in which they agree, which we denote the buffer region. So it's here that we match our two expansions. And one thing I really want to emphasize here is that the leading order, the most singular behavior of our external spacetime is constrained by the multipole structure of our small object. And here I bring extra notice to this term here, this epsilon squared over r squared, because this is the most singular term that the highly regular gauge seeks to eliminate. So from matched asymptotic expansions, as I mentioned on the previous slide, generically the singular field goes like 1 over r squared. And this is true of all previously used gauges in cell force, such as the Lorentz gauge has been mentioned previously. But at the moment, we are looking at if the small object is non-spinning and spherically symmetric, so we can describe it by the Schwarzschild metric. Now, in ingoing Eddington-Finkelstein coordinates, we can write it as so. So you can see straight away that this is linear in 1 over r. So if I go back here, this term is just 0. So h squared now only goes like epsilon squared over r. We've eliminated the most singular piece of h squared. In fact, if we impose light cone gauge conditions on the inner perturbations, we actually eliminate capital H1 as well, so that HS2 goes like r to the 0. Unfortunately, there are some problems with the light cone gauge. It's not easy to implement numerical schemes in this gauge because it constrains the regular field to go like r squared. But we can find a practical gauge where HS2 goes like the first order regular field divided by r. And although we have a singular nature, this is still much better than any previously considered gauge. We refer to this practical gauge as the highly regular gauge. In fact, it's actually a class of gauges, but we just refer to it as the highly regular gauge for the moment. To transform from the light cone gauge to the highly regular gauge, we split up our gauge transformation into singular and regular pieces. So one of the conditions we impose on our gauge transformation is that Z is smooth. So we see here, so we see here anything that is the Lie derivative of something smooth, such as the background metric or HR1, we put into the new regular field. And anything that is the Lie derivative of something singular, we put into the new singular field. This makes sure that we keep a split into singular and regular fields. So here we have our light cone HS2, which goes like order r to the 0. And it's this term here that we seek to calculate, which will go like order 1 over r. So to find the form of the gauge vector, we wish to solve this equation here. So HR1 on the left-hand side is undetermined. It's something that you can fix with a puncture scheme, but we want to write Z in terms of this HR1. So to solve this equation, we expand in powers of R, and then we coefficient match at each order in R. So as I said before, we solve for Z as a function of HR1. So we only impose 2 gauge conditions on Z. One is that it's smooth, and the second is that it preserves the position of the world line. So physically, we can think of this as ensuring that we don't introduce a mass dipole moment. So this is the same as saying that so the spatial parts of Z vanish on the world line. So I should mention as well that we're using Fermi-Walker coordinates. So we need to go to order r cubed in Z. This is because both the singular part and the Lie derivative both reduce our calculation by 1 order in R each. So to get order R in HS2, we need to go to order R cubed in Z. So now that we've found Z, and it's process by which we just match at each order in R. We can then perform the gauge transformation that we previously discussed to the highly regular gauge. Here, because HS2 and HS1 in the light cone gauge are already known, we can just perform the leader, act on HS1 light cone with the lead derivative with respect to Z. So unfortunately, I can't include the full expressions here because they are prohibitively long, but they will be available in an upcoming paper. One final thing that needs to be done before they can be used in a puncture scheme is that they need to be made covariant, and that would be using the techniques in this paper in Pound and Miller from 2014. We only have them in component form at the moment. And then, as I said, we can use the singular field as an input for a puncture scheme, as Adam discussed the puncture scheme previously in his talk. So we solve this coupled set of equations here. So the other benefit of our HS2 now going like 1 over R is that we can define things distributionally in the highly regular gauge. Now, generically, D2G has this form. So we have H times the second derivative of H plus a derivative of H times by another derivative of H. So because HS1 goes like 1 over R, we can just see by order counting that D2G of HS1 goes like 1 over R to the 4. So this is a very strong divergence. It's non-integrable in a distributional sense, so it causes a lot of problems. However, if we split up our new singular field into 2 pieces, into a singular times regular piece, which is M times the regular field divided by R, and a singular times singular piece, which goes like M squared R to the 0, then we can define things distributionally. So to see this, we know that because HSS goes like R to the 0, the DG, which we can think of as containing 2 derivatives, ensures that DG of HSS goes like 1 over R squared. But this term on the right-hand side is the only term that can source DG HSS. So this means that D2G HS1 in the highly regular gauge must go like 1 over R squared. So this is perfectly integrable in the distributional sense, so we can define it at all points in our space-time, crucially, including R equals 0. So with that defined, we know that we can cancel the most singular parts. We know that we have no trouble with the most singular parts because they're not actually as singular in the highly regular gauge. So we move on to HSR. Now, HSR is sourced by D2G HR1 HS1. So this is goes like 1 over R cubed. However, if we define D2G, this term here, as a linear operator, Q, acting on HS1, well, HS1 goes like 1 over R, which is an integrable function. And then for distribution theory, we know that a linear operator acting on an integrable function is well defined as a distribution. We can well define this term and this term as distributions. So at the moment, this is only true for R greater than 0, but we can extend that because we know they're valid as distributions. So the second order Einstein field equations for R greater than 0 become this. They're vacuum off the world line. So I've written D2G HR1 HS1 as Q HS1 here. But all these terms are well defined as distributions, as we've discussed. So I should note here that because this is the regular field, whenever we act on it on a distribution, it doesn't become more singular. So this is well defined. Act on it with a derivative, it doesn't become more singular. So this is still well defined as a distribution. And then I've combined all the H2s here just for visual clarity. So this is only true for R greater than 0, but everything is well defined as a distribution. So we can write that for all R, this term on the left-hand side is just equal to some energy momentum tensor, or stress energy tensor. So now to find T2 in the highly regular gauge, we find it in terms of the transformation from the light cone gauge. Now in the light cone gauge, T2 is actually 0. You can find this through explicit calculation. So T2 in the highly regular gauge is just the lead derivative of T1. T1 is invariant under gauge transformation, And this is a calculation that has already been done in terms of the gauge vector in this paper here. So we take the next step and we express the gauge vector in terms of our HR1 in the highly regular gauge, which we have found through our highly regular gauge transformation. And this is what we get for our final expression for T2 in the highly regular gauge. In fact, the total T, if we combine T1 and T2, can be written in this form, which is just the stress energy tensor of a particle moving in an effective spacetime. So if you recall, the effective spacetime is defined as the background metric plus the regular field perturbations. And this is the spacetime that dictates the movement of the small object. Now, this confirms Detweiler's conjecture that was made in this paper and is the reason that we refer to T2 as the Detweiler stress energy tensor. So this can also be extended to the Lorentz gauge, but there's quite a lot of subtlety required. So with the limited time I have, I'm not going to go into it. We also don't know how useful this will be, but we do have it that this T2, that this expression is also true in the Lorentz gauge as well. So to summarize, I've demonstrated how strong singularities near the small object can be alleviated using the highly regular gauge. And then described how the highly regular gauge can be used in a puncture scheme to calculate the regular field in the equation of motion. This highly regular gauge opens up avenues to mode-sum regularization and Green's function methods now that we have a well-defined T2. And we've also rigorously defined the Detweiler stress energy tensor, which is nothing more than that of a point particle moving in the effective space-time G tilde. Thank you.
Thank you, Sam, and perfectly within the time. So lots of time for questions. I'm not sure if that was what you were aiming for, but you're going to get it anyhow. Anyone with a question? Let's see if there's anything in the chat. Aaron, yes, go ahead.
Hi, yeah, great talk.
Hi, thank you.
So you emphasized at the beginning that with Schwarzschild, you have the benefit of moving into these coordinate systems where the metric around the black hole is well behaved. But then I lost track. Is everything you said here, does it only apply to Schwarzschild? These seem like statements that should apply universally, especially the last Detweiler stress energy tensor.
So we believe that they do apply universally. It's just specifically we're looking at Schwarzschild at the moment. I don't think, I'm not sure if T2 would be exactly the same in Kerr as well, because you might have some...
Right, with a spin part or something.
Yeah, with a spin correction, but it certainly seems like in Schwarzschild, this is exactly what you get.
Is there an obstruction you can see right away to what would make this hard to extend to Kerr?
I think, so we don't have a second order, I think the matched asymptotic expansions haven't been done yet for when the small object is described by the Kerr metric. It's actually something that I'm going to be working on after this project. So hopefully this is something that can be extended directly into that regime.
Okay, thank you very much.
Any other questions?
I can't figure out how to raise my hand as a co-host.
Oh yeah,
Okay,
sorry,
go ahead,
you
then.
can't.
But just one comment on the question. The matching actually has been done to this order, and yeah, you just add the usual test body derivative of a delta function. It's the next order that the matching hasn't been done and that Sam will be working on.
Thanks for the clarification, Adam. Anyone else? Because we did. Yes, great. Adrian, go ahead.
Yes, hello. Thank you very much for your talk. I have a question. At the last slide, when you consider this effective spacetime, what's the order in age, in the perturbation age that you have to consider? The first or the first and the second?
Oh, so this is going through the second order, but
Okay.
because so I sort of excluded my epsilons here, but this would actually be HR1 plus HR2, but we only actually see HR1 appearing in this expression. It's because T0 vanishes, we automatically get an epsilon in front of here, so that we don't need to consider the second order HR2, because that's higher order than anything that we're worried about.
Okay, thank you.
Hopefully that makes sense.
And I saw a raised hand from Takahiro.
But yes, I don't have an urgent question. It's okay.
We still have 2 minutes for questions, so feel free to ask.
Okay. So then, so in harmonic case, what kind of bad behavior of the second order perturbation appears?
Sorry, I missed the first part of your question.
So when you write down the second order perturbation in harmonic gauge, Lorentz gauge. So what kind of bad behavior appears?
So it generically goes like 1 over r squared. So whenever you operate on it, so specifically, really a lot of the problem comes from D2G. So this becomes very singular. So DG applied to HS2 goes like order 1 over r to the 4, which is very singular. So that causes a lot of problems when integrating things near to the world line.
Excellent. If I don't see any more questions, or did that answer your question?
Sorry,
yeah, I think so.
Okay, great. In that regard, let's thank Sam again. And we'll ask Zeyd to start sharing his screen. Is that? Are you able to share your screen, Zeyd?
Oh, hello.
Ah, great. We hear you at least. That's one.
Great. That's the first step. Share screen. So I think we should be getting something now.
Yeah, something's happening. Yes, great.
Excellent.
There we are.
Whoopsie.
Well, the floor is all yours.
Thanks very much. So thank you, Beatrice, for chairing this session. And thank you to the other chairs, of course. And thank you, Aaron, for organizing this meeting for us so that we can take part, given the circumstances. And of course, I'd also like to thank Jordan Moxon, Aina Flanagan, Adam Pound, and Jonathan Thompson for a project we've been working on in collaboration. And in particular, thank you for giving me the opportunity to give this talk on behalf of our work. I'd also like to acknowledge Tanya Hundra for excellent discussions while I was visiting the University of Amsterdam. And I'd like to thank the entire Grappa group there. So with that said then, I'd like to talk to you about energy and angular momentum. Sorry, by the way, are we full screen? I don't think so.
Not quite, no.
Oh.
I mean, the slides are clear, but we're not full screen.
Okay, if that's fine then.
Yeah, it's fine. Don't worry about it.
So I'll tell you about energy and angular momentum balance laws and second order self-force theory. So balance laws then, what do I mean? What I'm talking about is flux balance laws. So for orbits in Kerr, we're interested in fluxes of energy, angular momentum, and Carter constant, right? So these are the slowly evolving constants of motion during the slow in spiral. So what Galtsov gave us in the early 80s was leading order balance laws for ENL and perturbation theory. And what these enable us to do is to evolve generic orbits in Schwarzschild or equatorial and spherical orbits in Kerr. So why are we restricted? Well, that's because we didn't have a result for Carter constant. So what happened then was a nice result for the Carter constant really came following a breakthrough idea by Mino in 2003, where where a result was found for the for the rate of change of the Carter constant at leading order.
And everyone who's joined so far in about 5.
It's fine.
All right, so what was I saying? Sorry about that. So following a breakthrough idea by Mino, we have the leading order evolution of the Carter constant. And this followed about 20 years after Galtsov. So what happened following work by Sago et al. And Hughes et al. Was that we now have a scheme for generating waveforms, at a practical scheme at adiabatic order. And look out for forthcoming papers by Hughes and Warburton, as well as Fujita et al. On how to actually implement for the first time this adiabatic waveform generation scheme. So then, a major goal following this work has been to extend these results to post-adiabatic order. So what's being done? Well, people such as Miller, Pound, Warburton, Wardell, in their landmark paper from last year, they are currently calculating far more than is required at second order, and it's only applicable in Schwarzschild. So they get the conservative, the dissipative, they get averages, they get all modes, they get everything. They get far more than you need. So this is what Adam was hinting at. So what we really want is something more efficient and more streamlined. We really need to speed up these calculations. And for more background, I'd refer you to Adam and Lior's review. So then, as Adam was saying, the name of the game is second order cell force. And what we do is we expand our physical space-time metric in the background, Kerr in this case, plus a perturbation. And scaling arguments suggest that we really need to work to second order to reach the stringent accuracy requirements required for LISA. So this scaling argument was made more precise by Henderer and Flanagan. And what we see is that the expansion of the waveform phase, we have this term, the so-called adiabatic order term, and we have the post-adiabatic order term. And for now, just ignore this term here in the middle, as it's to do with resonances, which we ignore in our analysis. So that's for follow-up work. So then to calculate the adiabatic term, we require the average of the first order dissipative cell force. To calculate the first post-adiabatic term, we require the full first order cell force and the average of the second order dissipative cell force. So really, this is what Adam was saying. The second order dissipative cell force is just as important as the first order conservative cell force. So again, just to recap very briefly what Adam was saying, what do we actually do? Well, we want to work in a 2 timescale approximation. Why is that? Well, because because the 2 timescale approximation is really tailored to the disparate timescales in an emery. So you have the slowly evolving radiative end spiral over the radiation reaction time, but you also have the more rapid orbital timescale over an end spiral. So the system parameters for such an end spiral would be your energy, angular momentum, Carter constant, as well as the mass and spin, which can be handled in a 2 timescale framework. And what we have here is an action variable JA for these system parameters as a function of this slow time, epsilon t, where t tilde is epsilon t. So, sorry, I can try to full screen if that helps. Whoopsie. Well, we'll leave it for now. And psi A adjusts the phases. So once you have knowledge of these, where psi A give you the fast times and JA gives you the slow time, you plug them in and you can find a expansion, a 2 timescale expansion of your metric perturbation. So these H tilde here are the purely slow time evolving amplitudes. And what we want to do is compute the amplitudes and the phases through to post-adiabatic order. And ultimately, for practical evolution schemes, what we want is useful, that is to say, in 2 timescale form, perturbative expressions for these system parameters. And what I'll do is I'll focus on just 2 of these system parameters that we're interested in for our flux balance work, and that's the energy and angular momentum. you'll see that I've written it in a way that they can both be referred to simultaneously as in terms of some conserved charge, where they differ only by a sign, and that comes from the killing vector that we associate with this conserved charge. So that can either be the time-like or the axial killing vectors. But before I pursue this comment further, I'd like to say that we chose to work in an effective metric, which is what you see here. And I don't really know what people call this breva. It kind of looks like an upside down hat, maybe a cowboy hat appropriately, since we're supposedly in Texas, but nonetheless. So in this effective metric, we have our background metric, Kerr, plus the residual field. So remember, in an asymptotically small region around the small body, we can write the physical field as a puncture and a residual field. And outside of this region, the puncture goes to 0 and the residual field describes your physical metric, perturbation. So then, in the effective metric, these conserved charges, which represent E and L, can be written like this. So we're just contracting the forward velocity with the killing vector. So then, with a view towards getting to fluxes and time rate of change, we write dq in the effective metric, d tau in the effective metric. So that's just proper time in the effective metric. I've skipped a lot of steps here, but really just to give you an idea, we write this as a covariant derivative dotted with the forward velocity, and taking that of the conserved charge, you see we have a g and a xc. So then, so one of the steps I missed was that you have u covariant u alpha will give you 0. That term drops out of the product rule. You're left with a covariant of this term. So that then can be written, given the elegant identity that we have, that this can be written in terms of half of the Lie derivative of the effective metric. But of course, the Lie derivative along a killing vector of the background spacetime is 0. So that leaves us finally with this. So we have a half UU in the effective metric, Lie derivative of the residual field. So then, naturally, fluxes refer to intervals in time. So what we can do is simply multiply the left-hand side by d tau hat dt, and we do the same to the left-hand side, picking up this extra factor of 1 over u hat t. And so then, are we there yet in terms of asymptotic fluxes? Well, no, nowhere close actually, because we still have this residual field, and this is a local quantity. So what we really want to write is things in terms of asymptotic quantities. So what we do is to try and relate this residual field to asymptotic quantities, an intermediate step is to write in terms of the radiative field. Okay, so the radiative fields for first and second order are just defined as the integral of the radiative two-point function against the effective source. And actually that's true in both cases, but I've gone ahead and replaced my effective source in the first order case with the stress energy tensor for a point particle. So that's a luxury we have in the, whoopsie. So that's a luxury we have at first order, but not at second order. So at second order, our source is not a delta distribution, but rather, rather an extended distribution, an extended source, I should say. So really, these definitions, the same holds for the residual fields, but there is a subtlety. At first order, we like to work with, instead of G-ret, we like to work with the Detweiler-Whiting regular field. And really, just to streamline the presentation, I've chosen just to stick with showing you the radiative fields here. But just remember that the retarded Green's function is the antisymmetric, the radiative two-point function is the antisymmetric piece of G-ret, where G-rad is equal to a half G-ret minus a half G advanced. So what we want to do is then to express the balance laws in terms of these fields by really appealing to the symmetry properties of the Green's functions. So the symmetry properties of the Green's functions are really major players here. So sorry, how much time do I have left? Not much.
You have 4 minutes of the 16. and then another 4 minutes in the Q&A.
Okay, so I should be fine. So then, we want to relate the residual fields to the radiative fields. Okay, bearing in mind that both satisfy similar looking relationships. Right, so we had the residual fields from the evolution equation that we were left with. So that was this right here at the bottom. And what we say is, okay, we're taking a time averaged operation over this, and the time average is over fast time phases, right? So we're averaging out these oscillations on the orbital timescale. So these averages can really be thought of as an integral. So you have an integral UU, Lie derivative, and then remember this thing is an integral GT. Okay, so the stress energy tensor for point particle takes the form UU, and that's really helpful here because we have a symmetry. We have UU, Lie derivative, integral UU. So using the symmetry properties that I alluded at of the Green's functions, they're really important here. And what we can do is we can write this entirely, this term entirely in terms of the radiative field. So these steps really made use of things like interchanging the integration variables and as I say, crucially, these symmetries. So a second order, we don't have this luxury. We don't have the convenience of having the stress energy looking like a UU term. Instead, we have an extended source, we have an effective source, and we have to try a bit harder. So what we do is we look at this combination in brackets here. Okay, so this combination does have the form that we require to make use of symmetry relations. So we have something that looks like the stress energy, Lie derivative of a retarded 2-point function, right? And we have an effective source. We have here the effective source, Lie derivative of the 2-point function, and H1. So H1 gives us that stress energy form that we wanted, the one that we utilized at first order. Okay, so of course, all I've done here is add and subtract the same term, right? So we've just added 0. So this term here in brackets gives us, so for the residual field at second order, this gives us 2 times the radiative field. At first order, we get just the one contribution, and then we're left with this volume term to deal with. And I've absorbed some local terms from HR1 into the left-hand side. Don't worry about them now, but they will show up later. Okay, so then we look at these contributions at the bottom of this slide individually and see how we can relate them to asymptotic fluxes. So what we do is we try to convert this HRAD contribution to asymptotic fluxes. What we can do is, and what can be done is relate this to Tucholsky modes. That's possible. And I would refer you to Akçay et al. From last year, where something like this has been done for similar flux balance laws, although at first order for spinning secondary. But what we want to do is slightly different. So I've chosen not to write it in that form here, and I'll anticipate the reason soon. So what we do is we write this UU Lie derivative HRAD term in terms of boundary integrals. And this is historically what has been done at first order. And so these boundary integrals, you'll notice we have the, we have the Einstein tensor here. We have the delta squared piece of the Einstein tensor, and this depends on H1 contributions. We have our Killing vector from before. And from the H2 rad piece, what we see is we have something similar. We have H1, H2, H2, H1. So I could have written this as 2 times the Einstein tensor, and then a 1 over 4 pi here, but I really wanted to just stress the similar structure and just write with a 1 over 8 pi outside. So what you should notice from this, just in looking forward, is that this is the only contribution from H2 that appears in our final balance law. This is the only place that H2 appears. Okay, so with these boundary integrals in mind, we move forward and we look at the other contribution, which was the volume contribution. So that volume term has been a mystery for a while. And as Jordan Moxon will have said in his previous Capra talks, it's been unresolved and really, wasn't sure what to do about it. So it really was a bit of a mystery. But right now, what we see is, thanks to Jordan, if we choose a very carefully defined Gothic metric G, which schematically just takes the form of the background metric plus H1 with no H2, then what we find is that volume integral can be written as volume integral in that Gothic metric, right? And this is just the third order piece. And okay, so I'm really skipping over a lot of steps just for the sake of time, but this is the third order piece of that Einstein tensor that we had before. Of this entire contribution. So what I meant to say was, what we've done is this effective source, we've written that as the expansion of the Einstein tensor in this Gothic metric, right? And what you find then is that this entire volume integral in this Gothic metric can be reduced to a boundary integral. So the entire contribution really just results in a well-behaved boundary integral. So then, adding up those contributions, and this is why I said I didn't want to write anything in terms of fluxes, we leave them as boundary integrals. We add up those boundary integrals, and we get a flux across delta V, right? So what we find then is that we have G alpha beta of G minus the linearized G alpha beta of H. So this is really removing the linear piece of G alpha beta and leaving us with the nonlinear G alpha beta, right? So we have the nonlinear piece of G alpha beta. We have the surface element, which depends on G, not on the background G0, but on the physical two-body G, right? So it's corrected by the perturbation of the small body. C beta, remember, was just the killing vector. And this actually, if you look at it, thinking about this as an effective stress energy, as an effective source, this is really the Isaacson form of flux, right?
Just
and
to
again,
remind you, you only have now 30 seconds left. That includes Q&A time.
Okay, no problem. So this is just schematic, and we have some local terms in HR1, which I mentioned before, and I'm just neglecting some slow time derivatives. So what do we do to actually drive an in-spiral? Well, we require inputs from a two-timescale expansion of the field equations. At first order, we require the full first order field. At second order, we only require mode amplitudes from the second order bioscalar psi4. We don't need the entire H2. We can get away with just using Tucholsky amplitudes. So finally, what have we done? Well, Galtsov and the 80s gave us leading order derivations for flux balance laws for E and L. We now have them at post-adiabatic order. And thanks to key steps from Jordan, we now have how to convert from HR to HRAD and how to convert the volume integral into a boundary integral. So these balance laws directly relate the rate of change of energy and angular momentum to quantities that we can calculate at infinity and down the horizon. And they also offer the opportunity for efficient two-timescale evolution and implementation of the equatorial orbits using second order Tucholsky and avoiding the entire metric reconstruction from the metric, right? We can just get away with mode amplitudes. So although this derivation is highly general in that sense, we can evolve generic orbits in Kerr because we're still missing the Carter constant. And this is a really fruitful avenue, I think, for future work. And I'm sure we'll hear about it in the discussion session coming up. So thanks very much for your attention.
Thank you. Thanks for updating us on the second order flux balance laws. I'm afraid we don't have any time for questions, but feel free to ask the questions on the Slack channel. Great.
Hi, everyone. I'm Riccardo from the University of Trieste. And today I will talk you about the perturbed Schwarzschild horizons in second order perturbation theory. This is part of my master thesis project that I'm doing at the University of Southampton with Adam Pound. So we briefly see the outline of this talk. I start with some motivations. We will see how to define the intrinsic metric and the surface area of the horizon. We chose to look at the event horizon and the apparent horizon of the perturbed spacetime, and we will apply the two-time scale expansion, and we will see some result. finally, we end with the conclusions. So the systems underlying our project are the MRIs, the extreme mass ratio ion spirals. These systems belong to the gravitational two-body problem. And here we see a picture with different regimes and different models for the two-body problem. And as we know, we could use the self-force theory for the MRIs. The future developments aim to get very accurate predictions. We will have the improvement of the ground-based wave detectors as LIGO and Virgo, and future missions, space-based missions as LISA will be able to detect gravitational waves from the MRIs. So we need also very accurate numerical models and theoretical models. So for the self-force theory, we need the second order in epsilon. And I just recall that with the self-force theory, we go beyond the test particle approximation, and so we have a very good physical model for the MRIs. We are interested in studying the central black hole. We need to study the central black hole to have a complete knowledge of the behavior of the systems. And we could achieve very accurate calculation. For example, here we see a paper where there is the way where the authors calculate the gravitational binding energy for compact binaries. In this paper, we find also the evaluation of the reducible mass done using the apparent horizon. So basically, we will do the evaluation of the reducible mass also for the apparent horizon, and we will make a comparison. So as I said, thanks to the second order, we could actually make a comparison between different parameters or different definitions of the parameters of the central black hole, for example, the mass, but also applies for the angular momentum. So let's start defining the horizon surface. We write the horizon surface by these coordinates, where RH is the horizon radius. So here we see the expansion for the horizon radius. At a zero order is just 2m, so the Schwarzschild horizon. Then we have first and second order perturbation that generically depends on time and angular coordinates. So the intrinsic metric on the surface is given by gamma AB. Here we have the G alpha beta, which is the Schwarzschild metric in Eddington-Finkelstein coordinates. We have H alpha beta, which is the perturbation metric, and for our purpose, it's expanded up to the second order. And then we have E alpha A and E beta B, which are the tangent vectors to the horizon. Just a note for the notation, I use the capital Latin letters for the two-dimensional angular coordinates, and as usual, the Greek letters for the four-dimensional coordinates. So we could write the area of the horizon thanks to this integral. And basically, we have to compute the square root of the determinant of the intrinsic metric and to specify the location of the horizon. The area is an interesting object not only for a geometrical point of view, but it is related to an important physical property, which is the reducible mass. We could relate the area to the reducible mass by equation 5. So when I talk about the area, we always keep in mind that we could relate these two quantities by this simple relation. And so we could evaluate up to the second order the area, and we get expression 6. And now, until here, these expressions are generically, this holds for both the horizons. Indeed, here we see two kinds of terms, the perturbation metric and the perturbation radius. These terms are the coefficients of a tensorial spherical harmonic expansion that we have done in order to solve the integral. So now we need to find the radius in terms of the perturbation metric. And we notice that we need the full LM components for the first order. Instead, for the second order, we just need the 0,0 components. So let's recall how to define the event horizon and the apparent horizon. We describe the event horizon as a congruence of null geodesics. If we call with k alpha the tangent vector to this geodesics, it holds in arm relation. But to know where it is the event horizon, we need to know the full history of the manifold. So basically, we suppose that in the late future, the spacetime will behave as a stationary spacetime. Then we trace back in time the location of the event horizon. Instead, the apparent horizon is defined at each slice of time. And on the apparent horizon, the expansion is 0. The expansion is this scalar that I call theta, and it is given by the covariant divergence of the vector field k. But here, k is another k. It's not the same as for the event horizon. Here is a null vector field normal to the surface, and it is pointing outward. So generically, these two cases are different. But in the exactus Schwarzschild manifold, the event horizon and the apparent horizon are the same surface, basically a two-sphere of radius 2m. So I could use this fact to fix the zero-order components for the k-vector fields. Let's see how to determine the location of the horizon. So first of all, I construct a basis. I use the vector field k, then I use the tangent vectors to the surface, and I complete the basis with another normal vector to the surface that I call n. This is a basis on the perturbed spacetime. So between the vectors of the basis, there's some relation that holds. I use these relations to fix the to find the form of the first and second order perturbation of each field. We are especially interested in the k vector field, because then we apply the specific relation for the event horizon and the apparent horizon to find the horizon's equations. During this calculation, I evaluate every quantity up to the second order in epsilon. So I end up with some expression where every field is evaluated at r equal to m, so on the background horizon. As we have done for the area, we expand all the quantities in tensorial spherical harmonics. And so finally, we are able to solve the equation for the perturbed horizons. So let's see the event horizon. At first order, we get this differential equation. This is a differential equation for the first order radius. And instead of the second order, we look at the L equal to 0 components because are the components we need to compute the area, and so the irreducible mass. We get a quite longer expression. But in the end, we could rewrite both the equation as equation 11. So basically here we have a differential equation for the radius, and we put in the term that I call with f all the other terms. This equation has a so-called teleological solution. We call it teleological because we have to impose some condition in the late future, and we've put some Kerr condition in the late future. Moreover, this solution is given in an integral form. So to understand where it is the event horizon at a given instant in time, I have to perform this integral. Instead, for the apparent horizon, we could immediately solve the equations. So at first order, we get equation 13. And so we have the first order radius in terms of the first order perturbation metric. Instead, for the second order, we get a very long expression. It is also much longer with respect to the event horizon one. So I show only the general structure. And this general structure is quite simple. Basically, we have two linear terms in the second order metric, and then we have quadratic terms in the first order metric. So now we have some solution for the event horizon and the apparent horizon. But for the apparent horizon, we have this solution that depends on the late future condition, and it is in an integral form. So to compare them, we have to make some further specialization. And so we think about the emeries, and for the emeries, we know that the 2-time scale expansion applies. And so I briefly recall what is the 2-time scale expansion. We introduce a map between our starting manifold to a new manifold with these new coordinates. Basically, we replace our starting time with 2 new times. And so we map every field in some new field that I label with a tilde, and that depends on the new 2 times. These 2 times are v tilde, given by epsilon v. It is the slow time. It gives the variation on the long time scale, and it is associated to the radiation reaction time scale. Instead, phi is the so-called fast time, and it is associated to the short time scale of the system, and so it is associated to the orbital timescale. Now we could make an assumption. So the fields are periodic in the fast time with a frequency omega, and they are also bounded in the slow time. So thanks to this assumption, we could make the following Fourier expansion. Here, now, all the dependence on the fast time is in the exponential, and if we think to apply a fast time derivative, so we could immediately perform the derivative. Instead, if we apply a slow time derivative, we just get an epsilon term. These nice properties allow us to make some expansion to our equation for the event horizon. This relation also applies to all the fields that we have seen, not only for the radius. But before to apply this expansion, I have to make another assumption, because we would like that this expansion approximate both the equation for the event horizon, but also the solution that we have seen. So we specialize our system to systems that evolve to have zero angular momentum and capital M as total mass at late times. And then we apply the 2 timescale expansion. So at first order, we get equation 17 as a solution for the event horizon. And since we would like to make a comparison with the apparent horizon, we apply the same expansion to the solutions of the apparent horizon, and we get at first order equation 18. These two equations generally looks different, but if we set L, M, and K equal to 0, we get exactly the same result. At second order, instead we get very long expressions, especially for the apparent horizon. So basically, it is useful to rewrite the solution like equation 19 for the event horizon and 20 for the apparent horizon. Basically, here I keep the second order linear in the linear terms in the second order metric, the slow time derivatives, and I extract from the sums the 0, 0, 0 terms. So now, if we look at this expression, apart for the sums that run for KLM more than 0, these two expressions differs only by the slow time derivatives. So these expressions show us that actually the event horizon and the apparent horizon behaves differently in time. And thanks to the assumption we've made, now we have a local expression for the event horizon. So let's see some numerical results. We plug some data for quasi-circular orbit in our expression, and we compute the irreducible mass for the apparent horizon that I remember we already could find in the paper by Pound et al. And we evaluate also the irreducible mass for the event horizon. We look at the difference of the second order because it is the only terms that differs. And we use a logarithmic scale here in this plot to see the order of this difference. We plot this against the radius of the orbits, and basically we have also a cutoff in this plot around r equal to 6.01, where the quasi-circular orbits break down. So we see that when we approach the ISCO, the difference between the masses evaluated with the event horizon and the apparent horizon becomes more different. Also, this difference is entirely given by these slow time derivative terms, because the quadratic terms gives just a contribution of order 10 to the minus 21. So if we look at this scale, it's very, very small with respect to the actual difference. Moreover, we could plug some data to understand a more physical quantity for this difference. And so we assume some mass ratio for our ion spiral. And we see that the maximum difference between the two masses is around 10 to the minus 8 solar masses. And so it's a quite small difference with respect to the masses involved in the system. So we obtain some first order and second order perturbation for the location of the event horizon and the apparent horizon. we use this expression to find the area and also the reducible mass up to the second order for both the horizons, and we've made a comparison. We checked also the consistency of all our equation with some simpler setup like Schwarzschild, Kerr, and bi-idea spacetime. And so now our future prospects are to compute the gauge transformations up to the second order. We could derive also the second order perturbation for the angular momentum, the other important parameter for the central black hole. And finally, we could study and compare our results maybe with other definitions of mass that we have in general relativity. And that's all, and thank you.
Thank you very much, Riccardo. Telling us about the perturbed horizons. Any questions? Yes, Eric. Go ahead.
Thank you, Riccardo, for a very nice talk. So there's something you mentioned quickly that I'm not sure I understood. So you say that you make an approximation where you assume that there's no change in angular momentum in your black hole during the in-spiral?
Okay, no. We assume that the system evolves to have zero angular momentum at the end. So basically, technically, this means that this term is zero. This is our assumption.
Okay, so you start with angular momentum and then you evolve toward no angular momentum.
Exactly. We end with no angular momentum.
Okay, but I thought all the formulas were derived around the Schwarzschild background. I see a lot of, M's and 2M's. I don't see any R pluses or anything like that. So can you clarify that?
No R pluses?
Well, so if you were working in a Kerr background, I would have expected, 2M to be replaced by R plus, which is the, the coordinate value for the Kerr horizon.
Yeah, this is for a Schwarzschild background.
Okay, so then I'm not understanding, because if you say you don't have angular momentum, so if you're saying that you're starting with angular momentum, you must be starting with Kerr.
Okay, the angular momentum initially is very, very small. So let me try.
Oh yeah.
Okay,
right.
this is the Schwarzschild manifold, and basically we assume that this is small angular momentum, because initially we could have angular momentum, but it is order epsilon or epsilon square. So basically it is inside this perturbation metric, our initial angular momentum.
Okay, understood. Thank you.
Okay, thank you. Thank you.
Thanks, Eric, for the question. I also saw another question from Aaron.
Yeah, if there's time. Thank you, Riccardo. I was just curious, the event horizon of dynamical black holes in a situation like this is not going to be smooth. There's always going to be a crease along the horizon where new generators are joining. And I would have thought that would appear in your formulas for the apparent horizon radius as divergence of some kind, maybe a really weak one in the LM sum. Do you have something like that in the LM sum, or does that not appear at this order?
So you were telling if for example, in this kind of formulas, we have some kind of divergence?
Not for the apparent horizon. The apparent horizon should be smooth, but the event horizon is never.
Well, for example, in the regimes of the quasi-circular orbits, I think there are not problems. I think for sure when during the plunge or during later phases of the ion spiral, we will have sure some problem, because we have the merger, and also I think these almost all these quantities appears also in the apparent horizon. So it's in some sense it's quite simpler, this expression for the differential equation. So basically, I think these terms are quite well behaved, and the actual integral we didn't try to solve the exact integral, so or to plug the data in the integral. Yeah.
Yeah, right. Yeah, no, that's very interesting. Maybe it's just that while the 2 timescale approximation holds, that you don't drive these creases into existence, at least in the approximation. Thank you very much. That
Thank you.
I'll leave it there.
Great, thank you. Ricardo, if you can stop sharing your slides, and let me thank you again.
Thank you.
The last speaker of this morning's session is Benjamin. Benjamin, could you start sharing your slides?
Yep, sure.
Great.
Yep, should be able to see that now. So thanks, Beatrice. Thanks to the organisers for giving me the opportunity to speak today. My name is Ben Leather. I'm Niels Warburton's PhD student, and this work has been done in collaboration with him and Barry Wardell. So we've seen from some excellent previous talks already how we are now beginning to practically calculate the second order self force. The major breakthrough with such a calculation came late last year with the publication of the first implementation to calculate the gravitational binding energy by Adam Powell, Barry Wardell, Niels Warburton, and Jeremy Miller. So far, however, the only implementation has been for circular orbits in a Schwarzschild background. So our aim, if we're ever to provide something practical for LISA, is an adiabatic waveform for the physically relevant scenario of a generic orbit in Kerr spacetime. So whilst this challenge is by no means insurmountable, it's extraordinarily difficult, and so we must make incremental progress towards it. To that end, I've been looking at how to extend this calculation to eccentric orbits, and today I will outline 2 new methods that will hopefully advance this calculation further, which is a whirl tube method for eccentric orbits with exponential convergence and an effective source method for the Tucholsky equation, which is at a more preliminary stage. So let's consider the second order problem. We have our field equations where we perform a singular regular split. In the metric perturbation, at first order, we have our very well defined point particle source. In the second order Lorentz gauge formalism, this is where we start to encounter real difficulty for the second order source term because it's non-compact, sourced by the first order perturbation, and will diverge very strongly at the particle. So we subtract an appropriate puncture in order to have a source that is smooth and regular enough for us to solve. So we define a whirl tube around the world line, and so we solve for this so-called residual field inside this whirl tube, since the punctures are such that they're only valid in the vicinity of the world line. And outside the whirl tube, we solve for a more familiar retarded field and can match the 2 fields at the boundaries. At first order in Lorentz gauge formalism, we have our point particle source, which is defined by the delta function, and the action of the differential operator we see here on this puncture actually produces the same singular term. Hence, we have exact calculation of this delta function, and the remaining smooth piece is what we define as the effective source. So the challenge of eccentric orbits is that this discontinuity in the punctures will now be time dependent and move through the libration region. So this is quite well illustrated by the animation on the right-hand side there, where you see the particle moving from a minimum radius to maximum radius labeled Rmin and Rmax, so from apoapsis to periapsis. And as such, we need to actually take a further Fourier transform. And at first order, this problem is well documented and understood. One can use extended homogeneous solutions, but this at second order, as has previously been explained in other talks, you can no longer use this as your source is non-compact and not simply confined to the libration region. So we require an appropriate scheme to solve this problem from the perspective of using a whirl tube with an effective source. To reduce the complexity of the problem here and maintain focus on the issues we have at hand, rather than consider a Lorentz gauge perturbations, let's consider a scalar field toy model. So here I'll consider a first order compact source with a delta function that is spread across the libration region when you take a Fourier transform, but consider it from the perspective of an effective source, so we can compare our results to extended homogeneous solutions. So we have our usual wave equation for the scalar field psi with a source that is essentially the Fourier transform of the delta function. We introduce an auxiliary whirl tube. We solve for the homogeneous equation outside with retarded boundary conditions, where we get exponential convergence, but it's inside the whirl tube we start to encounter problems. So the Fourier transform of the effective source from the time domain is anything but trivial, as I'll explain shortly. Furthermore, we only see algebraic convergence. This is mainly due to Gibbs phenomena when we encounter when we actually take the Fourier transform. So it's impractical for any real world application, and especially if you wanted to sample over a large parameter space. And just to emphasize, we have a compact source here. So despite knowing the puncture analytically, we don't have a closed form for its Fourier transform, meaning we have to do this numerically. Since the discontinuity is time dependent, this isn't trivial. And as far as we know, this precludes any use of a fast Fourier transform algorithm. This means we have to do it in Mathematica. We have to sample and numerically integrate over a finite grid and then interpolate. It's horrid. So to get the precision required, it's computationally slow. The C0 differentiability in the time domain effective source leads to Gibbs ringing, which is responsible for this poor convergence. Another issue, although not entirely unexpected, is that when you integrate back over the effective source, we actually excite acausal homogeneous solutions. So just to demonstrate this Gibbs phenomena, on the right is the effective source, and on the left is the derivative of the puncture field, one of the components that makes up the effective source. These plots of the time domain reconstruction are reminiscent of those shown in the outline of extended homogeneous solutions by Barak, Ori, and Sago. And this shall actually inspire us to come out of our own method to eliminate Gibbs phenomena that I'll outline shortly. The other problem of acausal homogeneous solutions was first encountered by Seth Hopper and Chuck Evans, and this is a plot of the particular solution found from integrating from the horizon. It's actually very similar to one shown in their paper of the odd parity gauge transformation from Reggie Wheeler to Lorentz gauge. And what you see here is this constant offset between real and imaginary parts, and it's indicative of the presence of some asymptotically constant amplitude homogeneous terms. So in their paper, they devised a method to remove these erroneous terms, which they called extended particular solutions, which we'll quickly review now because we're going to use it going forwards. So in our setup, we're solving for the regular scalar field with our standard effective source in the Fourier domain. If we integrate with retarded boundary conditions from the horizon to spatial infinity, so it's going to be left to right here, what you see is we actually excite an acausal ingoing homogeneous solution. So the procedure would be to subtract this homogeneous solution with an appropriate weighting coefficient. We label it lambda minus here in accordance with Seth and Chuck's notation, and give us a standard causal particular solution. We can do the other way from integrating from spatial infinity to the horizon. So this is right to left now, and excite another acausal outgoing homogeneous solution, and similarly subtract this off with an appropriately weighted coefficient that we call Capra plus. So we have two causal solutions. They must be equal and their derivative must be equal, so we can equate them to actually find these coefficients Capra plus and lambda minus. So if we look at the same plot as before, but with our standard particular solution now, you see that we've actually eliminated that constant offset, so actually removed any excited acausal terms. So what's left for now is to outline our new method for eliminating Gibbs phenomena, which we call extended effective sources. So the idea is that either side of the discontinuity, we form two smooth functions, SF hat plus and SF hat minus. And SF hat plus is a continuation of the function from R min through to R max through to R min, sorry. And SF hat minus is just the other way, continuing from R min up to R max. We can define the Fourier transform of these functions in the same way as before, but we should no longer encounter any Gibbs phenomena because these functions no longer have a time-dependent discontinuity. And since there's no actual time-dependent discontinuity now, we can actually use a fast Fourier transform algorithm to get these. So we argue, due to the analytic nature of these functions, that in the large limit of the Fourier sum, that these functions will be equal to each other at the position of the particle. And therefore, by extension, for any T of R, we can express the effective source in terms of these extended effective sources and capture their piecewise continuous nature by Heaviside theta functions as shown here. So when we do this, we find we now have something that's exponentially convergent. So these are shown again by the same plots as before, but with a new effective source where we no longer see any Gibbs phenomena. So how do we combine both methods into something that restores exponential convergence for our regular field computation? Well, we define in the Fourier domain extended particular solutions with extended effective sources. These will still have our acausal homogeneous solutions present, so we remove them by using the same weighting coefficients we found previously with our standard source. It's this step that's the most time consuming, And because we still have to compute our solutions with the naive effective source, we can then transfer these new extended particular solutions back to the time domain in the usual way. And our regular field will then be given by the weak solution, which is similar to the effective source before, expressed in terms of these Heaviside theta functions. But it's worth noting that despite their presence, we still have a regular field that is smooth and is at least C2 differentiable. So here's some self-convergence plots for the effective source. You see that the Gibbs phenomenon manifests itself with this algebraic convergence on the left-hand side. But with extended effective sources, we have something that converges exponentially down to a very low error. And now let's just compare what we've achieved with this method with other computations with same source and parameters. So firstly, the first plot here in the blue is a algebraically convergent retarder field going as n to -1. This is found with variation of parameters. So this is the really naive way of doing things. Secondly, you have the regular field here. This is computed with the standard, what I would be referring to as the naive effective source and the world tube. It's going as n to the -3 because we have a suitably higher order puncture. Next, we have exponentially convergent regular field found with extended homogeneous solutions. So this, we don't actually find the regular field. What we find is the retarded field with extended homogeneous solutions and subtract off the puncture to get this curve. But now finally, you see our exponentially convergent regular field with extended effective sources in the red. You see we do very well down here, down to around n equals 20. We get something that's a lot better, accurate, a lot more accurate, gets there a lot more quickly. But you'll note we have this flattening of the curve, which is due to some round off error, we believe, and probably due to some loss of precision when finding the weighting coefficients with this standard source. So we definitely believe this is something we can improve upon going forwards. And we hope to continue going forwards as well. So I shall briefly outline how we hope to extend such calculations to gravitational perturbations. So as was outlined in Andrew's talk earlier, as a second order community, we feel the best route to a second order self-force formulation for Kerr is through the Tucholsky formalism. So instead of applying our techniques to an eccentric Lorentz gauge formalism, which could be very challenging indeed, we shall look to find an effective source method for the Tucholsky equation. For this work, we've restricted ourselves to Schwarzschild spacetime, and so specifically are looking at the radial Bardeen-Press Tucholsky equation. And to do this, we're going to require very quick sampling over the libration region to do the similar integrations as before. Hence, instead of using the MST method, we'll consider another possibly more favorable approach based on the geometric framework devised by Seneguglu. So this, instead of using T-slicing or time-hive surfaces that extend between the bifurcation sphere and spatial infinity, we're going to use hyperboloidal slicing. So this is now shown in orange on the right, where we rescale the radial Tucholsky solution to the following. This actually transforms our radial BBT equation to an equation with a suitably short-range potential. So here, H is the usual, what is referred to as the height function. And for the numerical integration, what you have to do, we can always transform back to T-slicing in the libration region using the inverse of this transformation. So this is preferable as we already use this technique for current second order calculations. And you'll see, as you'll note, our Tucholsky code sees very good agreement with pre-existing data with a relative error to around 10 to -12 with data we previously have. Just as a brief advertisement, I should point out this code is soon to be available on the Black Hole Perturbation Toolkit as a numerical integration option for the Tucholsky package. And so to actually construct an appropriate effective source, we use high enough order Lorentz gauge punctures to compute a gauge invariant puncture for the Weyl scalar psi4 with the following expression. Given the code for these punctures were already available for second order computations, this is currently only for circular orbits in Schwarzschild spacetime. So as a comparison, we set up the following residual regular radial Tucholsky solution with an effective source in terms of the usual source and the puncture. Here, this new box operator is shorthand for the BBT differential operator with spin weight -2, sorry. And we already have some nice results for this. So you see on the left, this is a plot for the particular Y-scalar mode with the retarded field outside the world tube. And then once we go inside the world tube, we have our regular field, which is nice and smooth and C2 differentiable. And as a sanity check, we can add the puncture back on to the regular field, and it sees you cover the usual retarded field with that discontinuity. And on the right, you can see the L modes of the regular Y-scalar do indeed converge as L to the -2. So to just finish up, to conclude, so firstly, for the new world tube method, we'd like to resolve the bottleneck in the calculation of the weighting coefficients that currently slows us down considerably. Practically, this is far too slow, and we would like to extend this methodology beyond the realm of the scalar field to gravitational perturbations. So currently, we consider a Lorentz gauge eccentric formulation quite challenging, and perhaps impractical given the current director of second order formulation. Hence, we have a renewed interest in the effective source method for the Tucholsky equation. We would like to begin working on a second order calculation. It would serve as a nice comparison with the current calculation in Lorentz gauge and lay any groundwork for subsequent calculations with more complicated orbits and spacetimes. Saying that, we want to extend what we currently have to eccentric orbits so we can begin to implement our new techniques and perhaps compute some gauge invariant quantities for comparison purposes. So this will be like computing the speciality index with our regular Y-scalar. So that's everything I have to say. I'll stop there and leave the floor for any questions.
Oh, fantastic. Perfectly within the time. And also a nice talk.
Thanks very much.
That too. Any questions from the audience? Let's see. Some comments, awesome results. So that's indeed great. I don't. Flipping between the chat and the participant list. Great. Well, I think everyone is just very happy with your results and looking forward to read all the details in the paper.
Very kind of them. I think they're probably suffering having watched so many talks in a row, so maybe a break's good for everybody.
I guess so. Yeah, in that spirit. Well, thanks again for this very clear talk. And everyone, don't forget, please stay logged in to make Aaron's life a little easier so he doesn't have to admit everyone by hand again.
Yes, thank you very much for that reminder.
Yeah, and I guess, well, yeah, Aaron, I'll give the floor back to you.
Thanks a ton, Beatrice, for chairing that session. Thanks everyone for hanging in there. We'll start our break. We'll be back at 20 minutes past the hour, so 9:20 Central. I'm going to go ahead and share LIGO's announcement, which is a high mass ratio system, either a black hole with a neutron star or a black hole with a black hole. The neutron star is either the heaviest neutron star ever or the lightest black hole ever observed. The paper is available for everyone, so if you want to spend your break glancing it over, go for it. But we will begin the talks again at 9:20 Central Time. Thanks, everyone. Stay in the room, please. All right, I hope everyone is around. We'll get started very shortly, about a minute left. So that looks good in terms of the full screen.
Great, can you hear me?
Yes.
Okay, perfect.
Okay, hopefully everyone has returned from the break, so we're going to get started here. I'll be chairing these last two talks, then we're going to take an hour-long break and return for the discussion session, which Adam Pound will lead. Kicking us off is Mekhi Dhesi. I hope I didn't mispronounce that too badly.
No, that was perfect.
Okay, from the University of Southampton. Who is going to tell us about how to better understand LIGO's recent detection clearly, LIGO Virgo's detection. So take it away.
Okay, thanks everybody. Thanks for tuning back in. Yeah, I'm a first year PhD student working with Lior Barak and Adam Pound at the University of Southampton. And yeah, we've just had some super exciting news here from the LIGO collaboration, observation of the first unequivocally unequal mass ratio coalescence. So that's pretty timely for me, as I'm working on modeling gravitational waves from binaries in the case in which the bodies have an intermediate mass ratio. And we are collaborating on this work with Harold Pfeiffer and Hannes Rüther at the Albert Einstein Institute. So I'll just start with a little bit of background on astrophysically how IMRIs are formed and why we want to observe them. So an intermediate mass ratio in spiral can be formed in two ways. So either a stellar mass compact object, such as a stellar mass black hole or a neutron star, can collide with an intermediate mass black hole. So very funny that we've just seen a paper about something that could be this. And these IMRIs would have gravitational wave frequencies which are thought to be detectable with advanced LIGO. And the analysis of their waveforms should allow us to explore the dynamics of globular clusters. The alternative formation scenario is the collision of an intermediate mass black hole with a supermassive mass black hole. And these IMRIs should have frequencies that make them exciting sources for LISA. And their waveforms would allow us to explore the dynamics of galactic nuclei. So the detection of IMRIs would provide strong astrophysical insight into galactic dynamics and also fundamental knowledge on black hole formation and black hole morphology. So we hope that our approach will be able to model gravitational waves from both types of IMRIs in the same way. So I'll go on to talk about that shortly. But as most of us here know, binary systems are most often classified by the large mass ratio between the two bodies. So on one end of the scale, we have extreme mass ratio in spirals, and we've heard a lot about the advancements in second order cell force this morning and how black hole perturbation theory is being used to create gravitational wave templates for these kind of binary systems. On the other end of the scale, we have comparable mass ratio in spirals with ratios of roughly 1 to 1 to 1 to 10. And these kind of binary systems successfully now use numerical simulations to evolve the full nonlinear Einstein field equations. And it's standard for such simulations to be able to evolve the binary through tens of orbits in spiral and merger. However, as the mass ratio of the two bodies increases, the computational cost of the simulation also dramatically increases. So more quantitatively, the computational runtime in numerical relativity is believed to scale approximately equal to the large mass ratio squared. One factor of this comes from the evolution time of the system, so there being big M over little m orbits required to accurately model the evolution. And another factor comes from big M over little m number of time steps required per orbit. So a smaller spatial stepping also therefore requires a smaller temporal stepping as per the numerical courant condition. So due to the disparate length scales and the disparate timescales present in IMRIs, computational efficiency in numerical relativity is often lost, and it's hard to feasibly evolve the numerically evolve the system. Just for an example, so with a mass ratio of 1 to 10, a high resolution numerical simulation could feasibly take 100 days to run. And on this same scaling, if we move to a 1 to 100 mass ratio, this would then take 10,000 days or so to run. So we need a sort of an approach to combat this. And our idea uses a hybrid method, which will combine perturbation theory with numerical relativity, which we hope could dramatically increase the efficiency for binaries in the range of 1 to 1 to 1 to 10, and also extend to include mass ratios of 1 to 1,000. But there has already been extremely impressive work done on modeling mass ratios of up to 1 to 100, using state-of-the-art adaptive mesh refinement techniques, for example. And Lusto and Healy at RIT only last month published a paper where a 1 to 128 mass ratio binary waveform was evolved through 13 orbits before merger. And so this is a figure from their recent paper here. And you can see the various mass ratio waveforms plotted against time. And I think the turquoise here is the 1 to 128 mass ratio binary. And also Hirschman et al. Have been working on numerical simulations of binaries up to mass ratios of 1 to 100 using their Dendro GR code. And so this is a figure from one of their recent papers here, which is nicely showing the mesh refinement that they've been using. But our approach proposes to tackle the problem with a different approach, with a different method. It uses a combination of black hole perturbation theory and numerical relativistic techniques. So let me tell you what the overall idea is. We hope to construct a sufficiently accurate solution to the full Einstein field equations for the binary spacetime by matching an approximate analytical solution surrounding the smaller body to a fully nonlinear numerical solution everywhere else in the spacetime, so the light gray shaded region here. So in effect, a region around the small body is excised from the numerics, like a bubble around the smaller body in 3D. And inside this region, we will place an approximate analytical solution. And so the effect of this is to partially relieve the scale disparity, which was impeding the efficiency of the numerical evolution before. And in the full GR case, the approximate analytical solution around the smaller body will be formed from a tidally perturbed metric, where the tidal perturbations are, of course, a result of the presence of the larger body in the binary. So the final model will require a 3+1 evolution for numerical relativity, but we began by analyzing a scalar toy model. And this is obviously the simplest possible model that captures enough physics to be relevant without having to worry about the full Einstein field equations and the nonlinearity. So what we did initially was replace the smaller black hole with just a point charge, which was on a circular orbit around the Schwarzschild black hole. And this allows us to test the overall ideas of the matching procedure, which I'll explain in the next slide. But we therefore just began by solving a scalar wave equation in Schwarzschild spacetime with a delta point source. And the potential field and the source can then be decomposed into spherical harmonic modes as shown here, where the F is just the standard 1 minus 2m over r term in the Schwarzschild metric, and E here is just the energy of a particle on a circular geodesic. So this mode decomposition reduces the problem to a 1+1 toy model. Expanding the scalar wave equation in Schwarzschild spacetime, we get an equation which takes the form here at the top of this slide once it's been transformed to double null coordinates. And we now build a numeric grid in these characteristic double null coordinates as visualized here. So such characteristic grid evolutions in time are tried and tested numeric schemes. And I've given a reference here to the original work done by Luster and Price. We use a quadratic order finite difference scheme to evolve the field in vacuum. My grid size is given by h here. And so the global error when using the quadratic order finite difference scheme is of order h to the 4, which becomes a local error of order h squared. Such characteristic grid setups are convenient because they do not require as strict boundary conditions as commonly needed in Cauchy type evolutions. So on these initial rays, we put some initially false data. Here we set the field equal to simply 0 or better a Gaussian wave packet. And this initial data is the equivalent of adding an initial wave burst, so junk radiation, but this will quickly dissipate away from the particle, leaving behind the correct behavior. So as long as we're examining the field at a late enough slice of time, it should not cause us a problem. So the first thing we did was to put, as I said, just the scalar point charge on the circular orbit, and its world line is given by the red line here. However, as you remember, our idea involves excising a region around the smaller body. So we replace the world line with a world tube, as shown in the region here now between the two red lines. So this in our 1+1 toy model is representing the 3+1 bubble, the bubble in the 3+1 model I spoke of earlier. It's the excise region from the numerics. And what we do is we now numerically evolve the field up to the world tube boundary and then match it to an approximate analytical solution inside the tube. And this matching will determine unknowns within that solution. So what do we take as the approximate analytical solution? So in the toy model, the field we want to match across the world tube boundary is the retarded field, the appropriate physical solution to the scalar wave equation. So you can see some similarities here between what I'm saying and what Benjamin was saying in the previous talk. And we now basically split this retarded field into a puncture field and a regular field. So the puncture field component can be derived in principle to arbitrary order in delta R. By delta R, what I'm referring to here is the distance from the center of the world tube. And here it's given to linear order. So these are known coefficients. And a result of linear order in delta R is derived in a paper by Waddell and Warburton, and we started by looking at this. For the regular field, however, we use a Taylor expansion in distance about the center of the world tube. And as we're working in characteristic coordinates, this is then just transformed to distances in delta U and delta V. And the coefficients of that Taylor series, underlined in red here, they are our unknowns in the approximate analytical solution. So we solve for them by matching to numerical data outside the tube. And this is done at each time step. So along each null ray, when we meet the world tube, we then fit to determine the necessary information in the approximate analytical solution. So it can then feed into the next null ray. And very quickly, two methods exist to solve for these unknown coefficients. Simply, we can either just set the approximate analytical solution equal to numeric values of the field outside the tube at the minimum number of points required to determine the unknowns. Then we're just solving a set of simultaneous equations. Or we can use a larger sample of numeric data on each side of the tube, as I've illustrated here. And then we use a best fit type regression model, so just a standard linear least squares regression model to find best fit values for the unknown coefficients. So I'll quickly show you now some results from the toy model. So what I'm plotting here is a slice of the field taken at constant time, chosen to be halfway up the grid's evolution. And these oscillations here are features of the initial data, so the junk dissipating away that I mentioned at the beginning. I'm looking at an L equals 2, M equals 0 mode at a fixed resolution, given by H equals to 0.1. And what I've plotted here are three different world tube widths. My world tube is given by delta, which is then plotted numerically for three different sizes. I should mention quickly that the grid size and this delta, they're just measured in terms of the large black hole mass, which was set to be 1. So as you can see, I've done three decreasing world tube sizes. And this is a zoom in here of the central region of the field slice. And you can see as you decrease the world tube width, the numerical solution converges closer to this black line. And the black line is the full analytical solution in this case, because when we are working with a non-static mode, there exists a closed form analytical solution for the scalar wave equation in Schwarzschild spacetime. So this is a nice check on our code that you can see it's behaving as it's expected by reducing the world tube width, we're getting closer to the closed form analytical expression. But the world tube width will, of course, ultimately be fixed. And instead, what we want to see is increasing agreement if we increase the accuracy of our approximate analytical solution. And we do this by adding higher order terms in delta R. So my next slide shows, again, these three decreasing world tube widths, but then in the interior, what I've zoomed in to plot is the different results when we increase the order of the analytical expression. So here it's just leading order, and then quadratic order and cubic order. And you can see better agreement with and also faster convergence towards the fully analytical solution. So we can see that our code is behaving as expected here. The same behavior is also seen when we move to analyzing non-static modes. So here I'm looking at an L equals 2, M equals 2 mode. And now the field is obviously complex. So we can see these sinusoidal type oscillations when we plot either the real or the imaginary part. I have plotted the real part. But here there is no longer a closed form analytical solution to the equation to which we can compare our numerics. But instead we can compare the world tube code to the code where I numerically just evolved a point particle on a circular orbit without any world tube. And that's given by my gray line here. So it's reassuring again to see that there is strong agreement between the point particle code and my world tube code when I decrease the width of the world tube and when I take the approximate analytical solution to higher order. Now, I'd just like to quantitatively show the actual convergence rate when I've ran the code 3 times for different world tube widths. So the convergence test is done by looking at 3 widths at successively half the size, so exactly what I've been plotting previously. And a difference in the value of the field is then taken as per this formula here in the top left. So the value of the field is sampled along a fixed slice of the grid, and here I take it along a fixed radial slice, which I take to be the right world tube boundary. And so by performing this test, you can see a settled convergence index. And what I've shown here are the different convergence indexes when I increase the order of the approximate analytical expression inside the world tube. So linear, quadratic, and cubic have been plotted. And you can see a faster convergence, so a higher settled index as I increase the order of the approximate analytical expression. You might be wondering why these are non-integer indices. And this is, we think, simply due to the fact that the simulations that I've been running in the toy model have not been in the domain where the world tube is sufficiently smaller than the mass of the big black hole, nor the grid size sufficiently smaller than the world tube size. And this is due to my code in the toy model being run on Mathematica, so there being restrictions on the runtime and the resolution size. And so the higher order terms in the numerical errors are not as small as we would like them to be. But still, the improving behavior, the improving convergence rate is clear as we increase the order of the analytical model. So next steps. So the aim of the excision method and the matching procedure is to reach a sufficiently high order in the analytical solution to relieve the disparity of length scales in the numerical evolution, whilst also balancing the number of unknowns needed to solve for. And all this can be tried with our toy model. But up until now, as I mentioned, we've been working with a model that has been evolving the field using a finite difference scheme. But ultimately, our method in 3+1 will be run using the spectral Einstein code, or the AEI. So we have to now move to using spectral methods. So the next step is to test the matching procedures that I've been running so far and the convergence rates in a 1+1 model, but using spectral methods for the field's numerical evolution. So once we're confident in the architecture of that code and the matching procedures, we'll then transition to a 3+1 scalar model. And we'll also then include orbital evolution, so the radiation reaction force, to actually model the merger of the two bodies. And at this stage, we will then be able to start probing the numerical efficiency and also the runtime saving of this excision method. Because up until now, we've really focused our time and effort on setting up the architecture of the world tube and testing our matching methodology. But at this stage, we'll actually be able to quantitatively understand how much of a runtime we're saving with this excision method. And then finally, we'll move to a 3+1 gravity model, where the numerical evolution will then now be fully carried out by the numerical relativity group led by Harold Pfeiffer at the AEI using SPEC. And it's a little image, nice images from SPEC. But the 3+1 gravity case will require deriving an expression for the analytical solution, which is formed from a tidally perturbed Schwarzschild metric. And metrics of tidally perturbed Schwarzschild black holes exist in the literature, specifically by Eric Poisson, but we will need to use a coordinate transformation in order to put them into coordinates that will then mesh better with the numerics used by SPEC. So that will take some time and work. Yeah, so they're my roadmaps for the future. Thank you for listening.
Thank you very much for that great talk. Also right on time. We have a few minutes for questions. Any questions? Yeah, go for it, Leo.
Hi, very nice talk. I was wondering, do you have a sense of how large the excision region can realistically be made? Because I mean, I kind of worry that you know, the gradients of the fields in the vicinity of the excision region are still going to be like whatever is the length scale of the curvature around the excision region. So that's going to ultimately set your Courant condition and your, yeah.
Mm-hmm. Yeah, so obviously the ideal aim of the methodology, as I said, to relieve the scale disparity, is to make it such that the excision region is sufficiently larger than the smaller black hole, while still being smaller than the big black hole. But I think what will really restrict us on the sides of the excision region will be the order to which we can acquire the tidally perturbed black hole metric, to which order we'll be able to acquire it, because the number of unknowns in this metric will really expand greatly as we go up to higher and higher order. So I think it will depend on to which order we can analytically derive it, and then we'll also have to test the runtime as to whether a high number of unknowns really then start to impede the numerical efficiency of the code as well. Did that answer your question?
Yeah, kind of.
Yeah, so
I mean, I'm kind of interested in, you know, what kind of reduction in Courant factor are you going to get, or do you expect to be able to get?
Yeah, I'm afraid I don't think I can answer that clearly at the moment, because we haven't managed to trial efficiently by moving to a 3+1 model yet. We've been really restricted to just setting up the architecture of the world tube at the minute and the matching procedures.
Okay.
Yeah, I think I'd have to get back to you when we've done our next phase.
Thanks.
Okay, let's have Niels.
Yeah, I was just wondering, you say in your next steps, you'll first move to a 3+1 code and then include orbital evolution. I wondered, why is there a reason you want to do it in that order rather than include orbital evolution in the 1+1 model and then move to 3+1? Yeah,
it's a good question. I don't think there's a particular reason, except that we think just in 1+1, what we're actually trialing is the matching setup between the numerical solution and the analytical in the interior of the world tube. So this is kind of potentially independent of the moving smaller body. I think we could have included orbital evolution at the 1+1 stage. I think potentially just, yeah, after speaking to the group at the AEI, I think this is the way that we want to go with it, but I agree that it could have been included in the 1+1 as well. I think we just have to choose an order in which to make things more complicated, I guess.
Sure, of course. Maybe just to say that we've been trying to do that, or a version of this, for a while with Peter Diener, and I guess he'll talk about this on Thursday. And that has been hard to include the orbital evolution. So
yeah,
it might be easier at the 1+1 level before you move to 3+1. But that's just our experience.
Yeah, I suppose if we're finding it difficult to move to 3+1, maybe that's something to try first, and then our life might be easier if we've managed to do that in 1+1 before we then go to tackle 3+1. Yeah, but it would be great to listen to Peter's talk as well.
Jonathan, do you have a fairly quick question?
Yeah, it should be pretty quick. So you looked at how the accuracy varies with the width of the world tube. I was wondering if you had already looked at how the accuracy varies with changing the global resolution as well. I imagine as the mass ratio increases, the length scale associated with a large black hole will be quite large compared to the excision region that could be set appropriately far away from the small black hole. I was wondering if you had looked into that.
Yeah, we had looked into that. I think I actually have potentially a reserve slide on it here. So I hope I'm answering your question right. But yes, this is when we kept the world tube fixed and looked at what happened when we increased the resolution of the finite difference scheme we were using. So increased the resolution, decreased the grid size. Yeah, so we've seen visually, you can see here the improving match with the analytical solution as you go to higher order in the approximate analytical solution and decrease the resolution. We obviously also did convergence tests when we were looking at the convergence with resolution, and we were using a finite difference scheme that was quadratic in its order. So we expected to see a quadratic convergence. It was actually interesting that we saw a little bit of deterioration because of the world tube. So the resolution didn't actually behave exactly as we expected. I think that's quite detailed, so I decided to omit it from the talk. But ultimately, we decided to abandon these investigations because as we'll be moving to spec and the spectral code, obviously we should be expecting to roughly see actually exponential convergence with that kind of numerical evolution. So we decided to not explore this too much further in this case, but it should be interesting to see if we do get what we expect with resolution when we move to spectral methods.
Okay, thanks again, Mekhi, for that great talk. And let's move on to the last talk of the morning session, Abe Harte. Abe, if you can screen share.
Okay.
Great. All right, take it away when you're ready.
All right, thanks. Okay, so I want to talk about the cell force in a fairly general context. And what that really means is this sort of basic, almost ancient question of how do things move? And the part of this that makes it cell force is that we imagine we have some object that's coupled to some long-range field, and we want to understand, or at least take into account, how self-interaction affects that motion. So in answering this question, well, we know quite a lot, of course. And in GR, at least, we like to say that, okay, things move on geodesics. But the natural question is, of course, geodesics of which metric? So for a test body, there's only one metric to choose from, and an object moves on that geodesic. But once self-interaction is included, it's not the actual physical metric that an object moves on, but it moves according to the geodesics of some effective metric. And much of the cell force problem at a foundational level is really understanding what is this effective metric, and how does it differ from the physical metric? How do you compute it from the physical metric? So this talk is about trying to understand things like this, and going beyond linear order, going second order, going to third order, fourth order, etc., and not really being terribly specific about GR or other theories. Most of this is really applicable to nonlinear theories of all types. Okay, so what do we know about cell force at foundational level? We kind of have, after a lot of different results over more than a century of looking at this problem, at least some aspects of this problem, there's a kind of organizing principle which has come out. And this says that, well, if you know the test body laws of motion for your theory, for some object coupled to some field, then these test body laws of motion actually still work when you turn on self-interaction, when you allow for self-interaction. But the only difference is that all of the fields that show up in your equations of motion are replaced by some effective counterparts. So if you have a metric in your equation of motion, it gets replaced by some effective metric, G hat. If you have some electromagnetic field, it's replaced by an effective electromagnetic field, and so on. And so every cell force result that we know of can be viewed in this form. Okay, so just as an example of that, to make it a little bit more concrete, if you have a charged particle, then a test charged particle moves according to the Lorentz force law. So we have something like this, the charge of the particle, the electromagnetic field. But then if you turn on self-interaction, the only thing that really changes is that the electromagnetic field that you had originally gets turned into some effective electromagnetic field, F hat. And of course, the devil is in the details here of exactly what does F hat mean. But at this point, I just want to stick to saying that there's some sense in which the test body laws of motion are at least structurally preserved. The same thing happens in gravity. For a test body, you move on a geodesic. For a self-interacting body, you move on a geodesic not of the effective metric, not of the physical metric, but of some effective metric. And I'm denoting this by putting a hat over the derivative operator. And these kinds of results are true, not just sort of for the monopole equations of motion like this, but you can generalize them to include spin, quadrupole moments, and so on. In fact, all of the multipole moments. Okay. So results like this have been known for a while now, but there are still some central questions that you can ask, one of which is how universal is this organizing principle? How general is it that the test body laws of motion remain valid for some effective fields? And strongly coupled to that is really the second question, which I'll call the self-force question, or the foundational self-force question, which is, okay, if you have this organizing principle, you have these effective fields that describe how objects move, but what exactly are they? What is this G hat, or what is this F hat? And in certain limits, so the limits that people usually talk about, these sorts of, I'll call this a mapping that says that, let's say that you have some physical metric G, and then you turn that into some G hat that tells you how your particle moves. This is usually described as a regularization procedure. So it's something that gets rid of infinities that are in G and gives you a well-behaved G hat. But I want to make the point that actually none of this has anything to do with infinities, and the things that we call regularization procedures are actually singular limits of results which are perfectly well behaved for finite objects with no infinities. So the actual underlying physics has nothing to do with getting rid of infinities. And this talk is about sort of understanding what those procedures look like. Okay, so what is known, or just very briefly, what is known? The linear theory is understood. So if you have some object and you're, let's say, looking at what is going on in the first order in perturbation theory in GR, then the metric in which the object moves is not the physical metric G, but it's some effective metric G hat, which is a functional of the physical metric. And you compute this by saying, okay, you take whatever the physical metric is, and you subtract something off. And you subtract something off in a way which uses some particular two-point function, G. So usually this is the Green's function. Usually it's more precisely the Detweiler-Whiting Green's function. But the important point here is really just that this is giving you some kind of non-locality. So G hat is something that's non-locally constructed from the physical metric. But in the linear theory, this transformation is in any case linear. So now what I want to talk about is what happens when you go to a nonlinear theory, or if you turn on higher orders in GR or in whatever theory it is that you're interested in. And it turns out that all of the techniques that you use to understand what happens in the linear theory, they generalize almost immediately to the nonlinear case. And you can sort of write down what I'll call a Volterra series for how you find this effective metric that tells you how things move. And in the test body case, so without self-interaction, you just have the background metric. This epsilon is your perturbation parameter. So at first order, you have the thing, basically what I wrote down on the previous slide. You have the first order metric perturbation minus some integral involving a two-point function. And okay, that's the first order result. But now what happens at second order? You get something a little bit more complicated. you get the second order metric perturbation minus, again, some sort of 2-point interaction. And now this is a different 2-point function than at first order, so the G1 versus G2. But now you have something new as well. You introduce a nonlinearity in the relation between the physical and the effective metrics. And you have this, in fact, 3-point function which shows up. And one can keep doing this. One can go to higher and higher orders, and you get a rather nice pattern that emerges. So at first order, as I said before, you basically have a 2-point function and nothing else. At second order, you have a 2-point function, a 3-point function, and nothing else. At third order, a 2-point function, a 3-point function, a 4-point function, and nothing else. And this pattern continues to as many orders as you would like. If you now stick to one of these columns here, so let's look at the 2-point column, you have sort of this infinite tower of 2-point functions that are associated with the cell force problem. So G1, G2, G3, etc. These are the 2-point functions that show up at order n. But all of these can sort of be summed together and derived from a single resummed 2-point function. So I'm calling this the infinite order result. So this single 2-point function, if you have that, you can derive all of the G1, G2, G3, etc., just by taking derivatives with respect to your perturbation parameter with respect to epsilon. And this works for the 3-point functions as well. You can pack them all up into a single 3-point object. The 4-point functions all go into a single 4-point object, and so on. Okay, so what are these things? So what are these 2-point functions that you need to use to understand the laws of motion? And well, okay, let's look at the 2-point case. So as I said, this is kind of just summing up all of the 2-point functions that show up at each individual order. But it turns out that this non-perturbative object on the left-hand side, from which all of the perturbative 2-point functions can be derived, is really just kind of an obvious generalization of this guy over here, of the lowest order 2-point object that exists, the one that we already know about, which is in most cases that you're interested in, the Detweiler-Whiting-Green's function. The only difference is that this non-perturbative 2-point function is the Detweiler-Whiting-Green's function not constructed on the background space-time, but constructed on the exact effective metric. This is kind of an implicit definition, but it gives you a very nice, simple way of constructing these objects. Okay, so how do you actually characterize this? So in order to derive the laws of motion, this object needs to have certain properties. And this is somewhat of a review, but I'll say that there are three properties that show up, one of which I'll call reciprocity. So this says that, okay, there are 2 points here, and the function is invariant under swapping those 2 points. X and X prime can be traded for one another with no penalty. This is sort of necessary for having kind of Newton's third law cancellations inside objects. Then there's second, there's a locality condition. This says that this 2-point function vanishes when its points are time-like separated. This is needed to ensure that renormalizations are physical, that they depend only on the structure of the body, the state of the body, where it is right now, and not what it was doing a week ago or a week in the future or anything like this. We have that condition. And then lastly, we say that this thing is a Green's function. So in the Einstein case, we say that the linearized Einstein operator acting on G is a delta function. All right, so that's the 2-point object. Now the new thing, or the more new thing, is this 3-point object. And it turns out that this obeys very similar constraints. So we have a reciprocity condition, and this says that, okay, we now have 3 points, and these can be permuted arbitrarily. We can take any of these 3 points, change them around, and this distribution stays the same. We have a locality condition, and now this is rather more difficult to visualize than in the 2-point case, but you have 3 different points, which means that you can form, you can look at the causal character of 3 different pairs of those 3 points, and ensuring that renormalizations are well defined requires that at least 2, that this thing vanishes if at least 2 out of the 3 pairs are time-like separated. So that's, again, very similar, but more complicated to the 2-point case. And then lastly, we put in sort of a second-order Green's function sort of constraint. Okay, so I don't want to get into a lot of detail about why these conditions here are important, or why they allow you to derive the laws of motion. But I do want to give one sort of nice physical idea that does come about. And that's to say that one of the things that you use in this is that you have kind of versions of Newton's third law that show up. And for the 3-point function, what some of those conditions are doing is to ensure that you have sort of a 3-point version of Newton's third law. So if you recall, the normal version of Newton's third law says that for every pair of points inside of an object, the net force and net moment of those pair of points has to be 0. So a 3-point version of this says, okay, take your body, look at 3 points inside. Then the force on the 3-point propagator says, okay, that determines, let's say, the force on this blue point due to the pair of red points. It talks about, okay, then the force on this blue point due to this pair of red points, and so on in the last way. And these forces are not decomposable in terms of pairwise forces. But the idea is that in the end, when you include all of these things together, the net force and moment has to be 0. Now, this is a bit of a bit of cheating, but this is roughly the physical interpretation of what physically or what mathematically comes out as saying that that Lie derivatives of these 2-point functions or 3-point functions or 4-point functions are equivalent to 0. So this this twiddle here means it's sort of a 0 in the sense of an equivalence relation. Basically means that the forces that are produced by such objects are removable by renormalization, by finite renormalization. Okay. So one last thing that I want to say is to talk a little bit about, okay, what do these functions look like? And for 2-point functions, we know what the singular structure of these things, we know the singular structure of these things. So we have a Hadamard form, which says that we have a delta function basically on the light cone, and then a step function that gives you a smooth support outside of the light cone. So the question is there something similarly intuitive for the 3-point functions? And the answer is that I haven't worked it out entirely yet, but it seems to be very close to what's occurring here. And you have, so now you have 3 different points, and you can build things that don't just depend on distances between points. And in fact, what it turns out to be important is that this thing looks like kind of 1 over the area of a triangle that's formed with the vertices of the 3 points. Or at least that's what this expression would be if we were in a Riemannian as opposed to Lorentzian setting. And then the numerator here is giving you the correct causal character. But again, this is not complete. There are some details still to be worked out. Okay, so just to conclude, what I've said is that if you look at the motion of bodies, and this is really in quite a general context, this works with arbitrary size and structure, and it works to all multipole orders. As long as you can apply a nonlinearity expansion, what comes up is that you introduce a bunch of endpoint functions, and these generalize in quite a natural way the 2-point function, the Green's function of Detweiler-Whiting. Okay, so that's what I said. And then what are some things that are left to do, or the many things left to do? One of which is just how can we actually construct these functions in a practical way? So is there a sort of Hadamard form and so on? And then sort of my more speculative comment here is, can this be put into a framework that's sort of similar to what you have in quantum field theory, where each of the endpoint functions is kind of a appropriate number of functional derivatives of some partition function, which maybe you can just compute once and for all. So that's maybe that's true, maybe not. And then another even more speculative idea is that perhaps this can be used as a sort of stepping stone to come up with a formulation which is fully non-perturbative, not even making use of a nonlinearity expansion, and you just sort of have a flow from the physical metric to the effective metric. Okay, thanks.
All right, thank you very much, Abe, for that really interesting talk. I completely failed in my chairship duties because I was paying attention to the talk and having to answer an email for the conference. So we're a little over, but I still want to give you time for questions. So Eric, please.
Yes, thank you. So you started out by saying that you can always define an effective metric or effective fields where the motion is as if it were for a test body. So have you proved this, or are you using this as input to construct the infinite sum over endpoint functions? So what's the logic of the whole enterprise here?
Yes. So the logic is if endpoint functions with these properties exist, then I can prove that the test body equations of motion are structurally preserved with the field replacements, as I said.
Oh, okay, so you're postulating the existence of that infinite sequence of endpoint functions.
Yes, so I just need some endpoint functions which satisfy these kinds of conditions, these three Detweiler-Whiting-like conditions.
And I guess you must also require convergence of the sum, right?
Yes, so this is in a sort of, this is a perturbative sense, and the sum might not converge, that's right.
Okay.
Other questions for Adam? Sorry, for Abe. Well, perhaps we can discuss further some of these ideas in discussion session today or tomorrow as well. So thanks once again, Abe, for the talk. Thanks again to all of the speakers from today. Really great talks all around, very exciting developments in nonlinear self-force. We're going to come back at 11 Central Time, so in 55 minutes, for a second order discussion, which is going to be led by Adam Pound. That will be in a different meeting room. So please check your email that I sent the other day for the Zoom link to that, or check the Slack channel for the Zoom link to that discussion. And I'll see everyone back in a new Zoom meeting room in about 55 minutes. Thanks, everyone.